of money. And perovskite solar cells, which are in the limelight for last 10 years or so because of their inception in 2009, now they have reached this much of efficiency, 26.3%, excellent efficiency, but suffer from severe instability. Like these cells, the lives of these cells is not very much, like 10 minutes, 2 minutes, 15 minutes, and they just get damaged. Like efficiency reduces because of the instability when exposed to moisture and heat. Because the materials which are being used in these perovskite solar cells are highly temperature and moisture sensitive. So because of that, their commercialization has not been done that much as expected, I can say. So as you can see that there are certain categories of cells in which work is going on, and efficiency and all the work we do, others do, is to get good efficiency. So that is called power conversion efficiency, right? How much, or another word is for external quantum efficiency. In other words, you can say that how much photons we are receiving and corresponding to how much photons we are, how much electrons we are creating, electron hole pair. So that is efficiency, right? So
Sir, your slide is moving. हाँ जी केबल लगाएंगे सर बीइंग ऑन द सेफर साइड दोनों चीजें चलाना और follow come to the cut. Not there. It's visible, sir.
just a minute. Am I audible now?
Yes, sir. You are audible.
So we, 2 minutes was for interruption, right? Previous slide, this one or what? Okay, let me continue with this one. Okay, okay. So as I was telling that in any solar cell there has to be at least one material in the, or in particular for this kind of solar cell where a p-n junction is to be there, a p-type material and n-type material, right? So what this antimony sulfide we are taking as a p-type of material. So there has to be some n-type material also, right? But this talk is mainly focused on p-type material that we are going to use as sp2 s3. But there can be different materials like cds, SNS2, Sb2S3. These are certain materials which can be used as a companion for p-type of Sb2S3, right? But what major characteristic one material should have so that it can absorb maximum number of photons is that its absorption coefficient, right? So only in this whole episode, or you can say in whole mechanism, the absorption coefficient of a particular material or the material to be used has to be very high, right? So that it can absorb good number of photons and can be used for converting the corresponding number of photons into electrons, right? So Sbs2s3 is such a type of material which is these days being used as a p-type material with CDS either, or stannous sulfide, or Sp2Se3, right? So these are Se3 means these chalconite, sulfide, selenite. These are the materials which are being used with Sp2S3 these days in producing a solar cell. And why these solar cells are getting interest of researchers? Because of their uh, band gap value has to be there. Band gap value, band gap, it is the band gap of any material that decides its absorbing capability, or how much photons or what category or what energy or frequency of photon a material will absorb, right? So okay, so and also there are certain materials in which their category as direct or indirect material band gap nature has to be also there, right? So direct band gap materials which involves photons, and indirect band gap materials of that involve phonon, right? So but this particular material has both natures at certain temperature. If the temperature varies, that material characteristic changes from indirect to direct. So basically they are direct band gap materials with a band gap of 1.7 electron volt, right? And absorption coefficient is around 10 to the power 5 per centimeter. They are versatile because of they can be deposited on means hard substrate, plastic substrate, or foils. And processability, they can be deposited. Their layers can be deposited with different techniques where temperature is up to 400 is only required, and no toxic materials is being involved. They are earth abundant, so these features make Sb2S3 solar cells uh, good for solar photovoltaics. And as I told you earlier, there is a limit to the efficiency that can be achieved with a particular solar cell. So that efficiency for this particular solar cell is only 28.64%. Means these cells cannot be utilized for, or cannot be investigated, examined for obtaining any efficiency more than 28.64%. Right. So that, but currently they are their efficiency that is recently reported is only 8%. So crystal structure of sp2 is basically orthorhombic with a stemnite structure, right? This is their structure in which a relevant type of structure is there which helps charge extraction, right? Charge compensation is also there, and lattice constants are 11.3 angstrom, 3.83 angstrom, and 11.2 angstrom. ABC values are these. And as we know that alpha, beta, gamma are going to be 90 degree for this particular. So highly they are highly anisotropic, as you know. So that anisotropic helps to get good physical and electrical properties in these materials. So architecture, if we go for these cells, the architecture can be of two types: mesoporous sensitized and planar heterojaction. Mesoporous means non-standard or unstructured configuration when is there. This is called mesoporous sensitized structure. And these cells also are of two types, which is one is called superstrate structure and other is substrate structure. So superstructure state is there from where the film from film side the light enters, as you can see in the next slide. At the bottom, light enters through the glass slide. So that is what superstate configuration. And if the light enters through the film substrate, then they are substrate configuration. So they both can be used. So like in these particular materials, what we have a transparent conducting oxide through which the light enters, and generally F2 and ITO are used. Mesoporous semiconducting oxide as titanium dioxide is generally preferred. Absorbing materials is Sb2S3. Like main absorbing material or activating material is what? This antimony sulfide, which absorbs photons and creates electron hole pairs. And there has to be a layer which is called HCl, hole transport layer. In certain materials, electron transport material is also there, and its job is to extract holes from the absorbing layer and make them move towards external junction, and there has to be a metal back contact also. Generally preferred metal contacts are either gold or silver. And other class of these structures are planar heterojunction structure, in which we have a metal back contact, as you can see, silver or gold. Organic materials, spiro omitted, P3ST. These materials are highly expensive, right? Generally used in perovskite solar cells. Other inorganic options are neon oxide, copper indium, copper selenide, right? Absorber layers that we can go for are uh, Sb2S3, Sb2Se3, and CDS, as I told you earlier, and ETA. Yeah. Second important component are these electron transport layers, which are generally preferred to be like cadmium sulfide, zinc aluminium sulfide, zinc oxide, titanium oxide, stannous oxide, and so many others. So this is basic structure. The total thickness of these structure has to be around 1000 nanometer only. 100 means 900 nanometer and equivalent. So thickness of these layers plays a very important role. You cannot have very high thickness or very low thickness. Thickness, if you take very small, what happens? You will not get good number of electron and holes. If you have very high thickness, there can be some impurity added to the material because of its making thicker, right? So that optimization of different parameters, like, and also, as you can say, p and n type materials are there. So general doping, as you know, is like one atom of impurity is to be added into 10 to the power 8 atoms of host material. But what happens generally during simulation, students or researchers, what do they do to obtain higher efficiency? They go for any limit of these dopants. So that has to be taken care of, that you cannot dope any amount of material to the host material. So that has to be checked. Thickness, doping density, and defect density, these are the parameters that have to be taken into consideration. So as I told you that if you have devices with electron transport layer or hole transport layer, then what happens? On x-axis we have devices with a hole transport layer, two cases, and devices without hole transport layer. So as you can see, the cell parameters like open circuit voltage or that short circuit current density, they are higher in case of when using devices with STL. Right. So this is suggested that if we go for these layers additionally, then we can have better enhancement in the solar cell parameters. So now you have seen that there is a substrate, the base material, on which different layers are to be deposited back to back. So what are the different techniques which are helpful in doing this? So there are certain classes of materials like some are solution-based techniques, and there are other like physical evaporation method. So chemical bar diffusion, which is generally called as CVD, spin coating, like material or the substrate is spin. The hydrothermal approach, chemical synthesis, that is pyrolysis, in which that the solvent is sprayed on some substrate. On the other hand, we have physical deposition techniques such as atomic layer deposition, thermal evaporation, vapor transport diffusion, closed space sublimation. So on left, the techniques mentioned are not that expensive, but that techniques mentioned on RHS right hand side, they are a bit sophisticated, more efficient, and expensive also. Right. So this is hydrothermal growth of that material to be deposited. So when this deposition is over, then what we have to do, there have to be certain additional jobs also. So post annealing, sometimes we need to do. So what annealing is something, annealing means heat treatment. So that what does it help, or how does it help? It helps to get the impurities eliminated from the surface of the material. So annealing is essential, right? And it also helps to enlarge the grains. So grain boundaries plays very important role. If you go for morphological study of these materials, you will find different types of morphology of these materials. So those morphologies are also very much important in deciding the performance of different materials. Right. So that is a different study that comes under structural features like XRD, SE, FECM, HRTM, whatever not. So there are so many things. Characterization. So to enhance or to have better performance, post deposition annealing is required. And also, as I told you earlier, that these HKL values, or orientation of material also plays certain roles. Crystal structure also plays some roles. So that has to be optimized. That has to be manipulated. That has to be modified in a way so that it comes in the way that it delivers more and charge transport is efficient. So this is further classification of different techniques like spin coating, formation of compact and uniform film. You will find from this chemical bar deposition is a very simple technique, but non-uniformity is a drawback of these materials, right? So these are the certain techniques in which deposition is possible, but certain merits and demerits are there. Okay. So, where do these SB2 S3 solar cells stand? So, reality is that their power efficiency, which is 8.0% recently, can go up to 28.64% only, right? With this band gap of 1.7 electron volt. So, there are certain materials which have band gap more than these. So, they are wide band materials. Certain materials which have band gap values less than that. So, but 1.5 is the ideal value to have more number of photons absorbed and converted them into corresponding electricity, right? So, but 1.7 electron volt is also very much justified for absorption of high number of photons. So, as you can see, SQ limit I have mentioned that it is 28.6%. So, these cells have to go a long way actually. Recent efficiency is only 8%. You can go up to 28.64%. So, these cells have to travel a long distance for to compete with the contemporary solar cells like cadmium telluride, or you can say perovskite solar cells or silicon vapor cells. So what are different challenges in getting that much of efficiency beyond 25%? There are certain challenges like intrinsic material challenges. They contain carrier self trapping effect are there, energy losses are there, defect physics is also there. Means while doping materials, certain defects, unnecessary or unwanted impurities are also added to the materials. So we have to take care of their low conductivity. Conductivity has to be high. Means we have to take care of these electrodes. Anisotropic structure and orientation control. As I told you that in this SB2 S3, what happens that chain or ribbon type of structure extends infinitely along C axis, right? So that had to be optimized. Thermodynamic preference for HK0 means HK values can change, but L value should be there 0. Requirement for HKL orientation is there. So these are certain requirements that have to be fulfilled. And as you can see in the bottom side, that how electron and that electron transport layer on whole transport layers play their roles, right? So they allow charge carriers to move away from the junction and constitute corresponding current. Defects, bulk interfaces are there, intrinsic and complex self-wrapping, and overall we have to see that good value, reasonable values of these solar cell parameters means short circuit current, open circuit voltage, fill factor, and efficiency we obtain. In that path of achieving very high efficiency, certain hurdles are there. So these hurdles are to be overcome. And also interface. So whenever two layers are there, they constitute an interface. So while passing from one layer to other layer, there can be so many other obstacles that charge carriers may face. So that we have to take care of because of deposition of layers over one other layer. Then what happens? Sometimes it happens that materials get leaked or just penetrate into the other layer. So that we have to take care of. And energy band alignment is also there. Means you cannot dope any material with any other material. Band alignment has to be there, right? Corresponding band alignment and adjacent band alignment are certain parameters that we have to check. Impurity information, morphological defects, as I told you that we have to see morphology, that uh, materials are of certain uh, shapes, sizes, and uh, gesture also. So what advancement these cells have seen in recent past is that crystal orientation control some people have done, some people have worked on interface engineering and also on defect passivation. So crystal orientation control means while treating these material or that antimony sulfide, we have to go for synthesis of material in a way so that the preferred orientation is dominating, right? Secondly, interface engineering means we have to have good interface Reasonable interface where charge transport is very easy, electrons and holes are not blocked, they are supported to get away from the junction. And also defect isolation means we have to treat the material so that defect from the surfaces are eliminated. As I told you earlier, orientation and grain. Uh, this slide suggests that how that morphology can be controlled. So by doing this, 6.82% of efficiency has been achieved so far, right? And other methods for their deposition involve vapor deposition, vapor transport deposition. So these methods support in or help in attaining good efficiency from the same material when orientation polarization is means orientation of material is optimized. Yeah, interface and ETL engineering means interface interfaces. At least you can understand there are two interfaces. In the between in between we have that absorbing material Sp2S3, another material as CDS, as I told you, as n-type material is there, and then we have ETL and STL both sides. So then these interfaces are to be very smooth. Smooth means they should allow smooth charge carrier transport. So as you can see, with this we can have good value of that J. J means current density up to around 23 milliampere per centimeter square. And also when CDS is a counterpart of that this Sb2S3 solar cells, then post treatment, as I told you, post annealing is requirement. So if we do that in presence of KCl, efficiency can be improved up to 9.98%. And also if we dope the ETL with this magnesium or zinc, then it also helps to attain good value of open circuit voltage. Defect passivation also helps to improve the efficiency. It has been reported that if we do that material with zinc, then efficiency can be improved from 6.35% to 6.56%. Surface passivation, removal of impurities from the surface, has also helped to achieve a good PC power conversion efficiency of 7.1%. And sulfurization has also helped to have efficiency up to say 8% in the 8%. Specific applications, if we go for these materials, these solar cells, so they are so as you know that single junction solar cell is there, it has a certain efficiency, a limit to its efficiency. But if we have a stack, if we have back to back so many solar cells, so that comes under tandem solar cells, right? So in future that these cells sp2 sp3 solar cells are going to be a strong candidate for tandem devices also as a top subcells because of their band gap values, and that limit can be reached up to 43%. So single junction solar cell, if you go for sp2s3 solar cells, the efficiency is limited with 28 point something value. But with tandem device, tandem structure, you can touch 43% marks also. And
Sir,
indoor,
sorry to interrupt. We just have 5 more minutes for the talk.
yeah, I'm just concluding.
Thank you.
So indoor photovoltaics means so far you have seen that these solar panels are installed on the rooftops, but there are other classes also, right? There are going to be bifacial solar cells. So not only these solar cells absorb energy from top, but they can absorb energy from bottom surfaces also. There are going to be flexible solar cells also, means you can fold them, you can lay down them, you can have any structure in with these flexible solar cells. So in the same category, there are going to be certain indoor photovoltaics also, which even absorb good number of photons in low light also, right? So sb2 s3 cells can be a part of that also, and also they can offer semi-transparent applications because of its band gap. Those who are new to this field, all we are discussing is just opposite to a solar cell. Sorry, a light emitting diode. A light emitting diode is given energy, electrical energy, and then we get certain light. Light is emitted, or but in the solar cell we give light and we get electricity. So solar windows means the time is not far that most of the buildings will be installed with these solar panels in future, and high amount of energy will be converted, solar energy will be converted into corresponding to electricity. So other contribution is our contribution as far as is concerned. So recently we have started working with this SCAS 1D simulation software, and we have taken SNS2, stainless sulfide, as the counterpart for SB2S3 films. So this SB2S3 is P-type and SNS2 is N-type. So this combination we are working on. Initially, we have gone for this structure in which FTO, and is going to be as the transparent conducting oxide, and then gold we have considered as the one of the electrodes. And we have what where we are working on, thickness, carrier concentration, band gap, electron affinity, and certain losses like defect density, resistive losses, and optical losses. As I told you earlier, and I am repeating that while before going for experimental work, these parameters have to be optimized. So this is because of that SPS23. If you go for its search, you will find that it is of orange color. So this is how it is deposited and how it looks, right? And recently we have taken this XRD pattern also, which is highly matchable with the standard or established XRD patterns of these SB2S3 field. We have recently optimized these key parameters, which are going to be published in a journal shortly. So absorber layer, we have taken as SB2, S3, I told you. Window layer, absorbing layer. Its job is complete to absorb photons and to transfer these photons to these SB2, S3 layer. Electrical properties with this band of 1.75. Electron affinity we have considered with 3.9 electron volt, and we have witnessed reasonable increase enhancement in the cell parameters. Doping we have taken care of. Doping we have gone for slightly higher side, 10 to the power minus 19% cubic centimeter. Optimized value is 1 into 10 to the power 17 cubic centimeter. Fill factor, as you can see, have touched very high mark. Yeah, we have gone for the model also, and series resistance and resistance values are also within the achievable marks. Yeah, these are certain parameters that we have calculated. Both layers are optimized with a value of 10 to the power 15 per cubic centimeter, and defect density has led to decrease in this carrier length and length. So this is the work that we have just submitted to this. Yeah. Yeah. So interface, I told you earlier that interface between two layers like SNS2 and SB2, S3 has to be very seriously monitored, and all the defects have to be kept within limit that are only enhancing the cell parameters, and that value of interface defect density is up to 1 into 10 to the power 13 per centimeter square. We have managed it. We have well managed it, and we have also we have worked on band alignment, CBO conduction when offset, VBO balance when offset. So these are certain values when you have to see that what band gap value, what band alignment we should go, and what we should not. Then these plays certain roles because of when materials are combined, certain changes occur. So these changes are to be in these terms only. So CBO we have witnessed up to 0.24 electron volt. VBO we have electron for witnessed for 1.5 electron volt. And these are the optimized device performance. So theoretically we have witnessed an efficiency of around 18.3% with a JSC of 18.95, VOC of 1.20 volt, and fill factor of 71.95. These are other parameters. Effect. Yeah, temperature also plays some important role in that. So to summarize, I can say that these cells, SB2, S3 solar cells, have the potential to become a major energy supplier in future. Like if the research on or in the investigation on these materials or these cells keeps on going in the same way, then very soon we will be crossing the 15% mark of their efficiency. And their current efficiency, as I told you, is either CDS or SNS2 or SP2S3 to form a PN junction. Before going for experimental work, optimization of different parameters is suggested because they will allow you or they will help you not to waste time for experimental work. After optimization of the parameters, you can directly go for the experimental work. Some measures that have been taken recently to modify or to enhance their performance or to achieve greater efficiency are like orientation control, interface engineering, defect passivation, controlling these defect parameters which I've had. These says to achieve a very high efficiency. Thank you.
Sir, Kajay? a very fascinating and deeply insightful presentation. Okay. And highlighting the potential applications of antimony sulfide-based solar cells. We are indeed grateful to you, sir.
Thank you, sir.
Is there any question? Yeah. Sir, there's a question from
Yeah,
Aftab.
please.
Sir, my question is how the morphology changes the efficiency of solar cell.
See, what happens if there are so many voids, so many defects, surface is not smooth, surface is having some defects, then morphology will not in this way the morphology is of this kind, then it will be not proper charge transport, right? So morphology has to be taken care of so that charges or electrons or holes flows very fluently through the materials. So in that way, and grain boundaries have to be very precise. Yeah.
How to control morphology in heterojunction?
Different methods are there. We can deposition parameters you have to check, like deposition time, deposition parameter, right? Solubility, even the impurity. You have once to start with the impurity of the purity of the material, right? So it is the purity, then temperature, then time. There are so many parameters to control and also capping agent. You can see if you go for nanotechnology or you are trying to find the materials in nano range, then there are certain other parameters that you have to take care of.
Okay, thank you, sir.
Thank you.
Sorry, question. So, if there is no question, sir, I have a small question for you. How do you control self-efficiency using hydrothermal method in anti-sulfate systems and the postal process also?
Hello. Yes, sir.
Am I audible, sir?
Audible, but partially.
Yeah. My question is control self while synthesizing antimony sulfide system and in its post-annealing process. Because generally,
Yeah.
sulfide system, mostly systems are sulfur deficient.
Yeah.
So how do you control it?
We
So,
expect that whatever we have done for optimization, and recently we have started depositing. That film has been deposited in last 15 months or 15 days only. So we have gone just for XRD, that validating that now the films have deposited. Now we will see that annealing has to be done at what temperature with in presence of what material.
I mean,
We have
annealing
yet not gone.
in some sulfur environment or
We have not yet done that. We will
okay,
go for sulfurization. We will go for that.
okay. Thank you, sir. Thank you for a nice elaborative talk.
Thank you, sir.
Okay, sir.
Hope to meet you soon.
Sure, sir. We would like to have felicitated you had you been here. So thank you so much, sir, for joining us.
Thank you. I can leave now?
Yeah, yes, sir.
Thank you
Sure.
so much. Thank you.
Thank you, sir. So, sir has joined. Okay. So we have second talk of the morning by Dr. Shubhadeep Datta. So we'll take you from the world of light energy to now the world of sound. So our second speaker is Dr. Shubhadeep Datta, who is presently working as Associate Professor at School of Physical Sciences, Indian Association for Cultivation of Sciences, IACS, Kolkata, one of India's most prestigious research institutions. Dr. Datta is an experimental physicist specializing in condensed matter physics. His doctoral works at CNRS Grenoble, France, focused on low temperature electrical transport in carbon nanotubes filled with magnetic particles. His postdoctoral stints at ENS Paris and the National University of Singapore, NUS, brought him into the frontier of molecular electronics and spintronics using two-dimensional materials like graphene. At IACS, he has built a fully integrated laboratory pipeline for two-dimensional magnets, from crystal growth and microelectronic fabrication to advanced transport measurements and Raman scattering. His current research explores pressure and strain driven transitions in single crystals, sound propagation through atomic layers, and ion electronic interactions in microfluidic devices. So, he will be talking on ultrasound assisted piezotronic transduction in microelectronic circuits. Sir, over to you, sir. You will have 30 minutes.
Thank you very much for the introduction. I hope my screen is visible to you, right?
It's visible. You can make it full screen mode. Yeah, it's visible now. And you
Okay.
are audible also. So you can start now, sir.
Thank you very much. First of all, thank you, the organizers of Fast SD 2026. A special thanks to my senior Professor Oyana Bhaduri, whom I know from my postdoc days in Paris. So the work which I will be presenting here, it's a very recent work which we have performed in our laboratory for the, let's say, from 2024. So it's like 2 year effort, 2024 to 2025, for getting these sort of results with ultrasound. So the title of my talk is Ultrasound Assisted Piezotronic Transduction in Microelectronic Circuits. From the last talk, you have understood that the thin films, how thin film solar cell behaves. Now, this talk will be on atomic layer systems. As you can see, if you see my screen and the pointer, yes. So I hope you can see my pointer. So this triangular region is the atomically thin semiconductor named as MOS2, molybdenum disulfide. And these yellow lines are electrodes. So this is microelectronic circuits, because the separation between these two electrodes are like of the order of microns, and the thickness of the this triangular region is of the order of 1 nanometer. Now, the main question which I want to pose is, what is the effect of sound on this tiny little region of van der Waals semiconductor? So that is why ultrasound will be propagated through this material, and then with these two gold electrodes, we will try to see if we can sort of detect piezotronic activity in these materials. So to start with, first I give you a short introduction of our group. So our research group concerned, starts with, research-wise, starts with single crystal growth of van der Waals materials. And technique we use Raman spectroscopy and fabrication of devices, which I will be showing you, and dielectric or transport measurements. The sample library which usually we follow is magnetic 2D materials, and the physics which usually we probe is coupling between lattice and spin. So, to be specific, spin lattice coupling. And then since we are using FET, field effect transistor, so that is why electric field controlled measurements are given importance, and controlling the magnetodielectric coupling with magnetic anisotropy. So dielectric coming because dielectric terms is coming here because we usually use magnetic 2D materials which are insulators. So to give you an example of these van der Waals materials, if you follow this GIF, as you can see, the contrast changes, and the contrast changes because there are different layers. So if you exfoliate a van der Waals semiconductor from a crystal onto a silicon oxide silicon surface, conventional silicon surface, then you would see that there are different layers. These are exactly like graphene, but it's sort of graphene sisters in semiconductor physics. And the circuit which we will be usually we probe is like this. As you can see, these are the gold electrodes, and usual dimension starts from, channel length starts from 10 micron to 200 nanometer. So this is one semiconductor. As you can see, this is all homegrown, and you can create lithography circuits at ISCS. So two examples of different circuits. As you can see, there can be CMOS fabrication with this. Our recent results show that a 1D nanowire and a 2D material, which I will be discussing, only this 2D I will be discussing, can be integrated to create a PN, so diode and a CMOS. Together with this, We can also create circuits with magnetic insulators, as you can see here, and you can measure magnetoresistance on top of it. So you can create, electron magnon, you can probe electron magnon coupling in devices. Just to give you a glimpse of our circuits, as you can see, this one has been already discussed. This is also a part of the our job to connect those circuits with electrometers. So as you can see, these aluminum wires, which you can see from here, will be connecting your chip to the meters. And examples of 1D circuits and 2D circuits, it's not only 2 or 4 probes we measure. We can measure something like 4, 6, 8, 10 probes of the order of channel length like 200 nanometer to 1 micron actually currently. So as I say, our lab works on crystal to circuit. So we can grow crystals and we can create circuits on different platforms. Now, coming to the main objective of this talk, why we are using ultrasound. So this is the triangle which you can see here: phonons, magnons, and electrons, right? So usually experimental quantum physicists, they are interested in one of these couplings: electron phonon, electron magnon, or magnon phonon coupling. So of course, we have, in our experiments, we have tried to probe different couplings like electrons, electron phonon, or electron magnon, as I have discussed this circuit, or magnon phonon coupling. So it's sort of lattice and electrons, lattice or spin waves. Now, to tune these couplings, you can use different functional knobs. So these are the functional knobs which you can use. For sure, we can use electrostatic gate or strain or pressure, electrostatic gate, or you can use different heterostructures. So you can sort of manipulate different orders, electrical, magnetic, or topological orders, to create a functional knob which will tune the coupling between these elementary excitations. So this is quite common in semiconductor physics, magnetism. But the point is, how about introducing another functional knob, which is acoustic field, so which is sound. So this is the new knob which we will be sort of introducing in the field of interaction landscape of quantum physics. Let's see. So usually sound, if you go back to the 1700, you will see that there are a lot of interesting experiments which started with sound. So this is one of the examples. Usually, they are termed as Chladni figures. If you have a vibrating string, and then if you can sort of create a platform, a vibrating plate. So if you touch it at different places, you can create different structures. So diagram of Chladni figures. This is something like 1700. You can, students can go through this excellent paper. This is sort of a review in 1982. I learned this, the calculations from this paper only. And then Boyle made an excellent experiment, dipping a clock inside a vacuum chamber and try to hear how the sound of the clock is getting changed if he lowers the air pressure. So that's the one of the first experiments, I think, with sound. And then Langevin, it's seminal work during World War One, ultrasonic capacitive transducer. So this ultrasonic transducer was used in the submarines during World War. So this is one of the finest work during that time. and Bernoulli's principle, because Bernoulli, during his, we usually study Bernoulli's principle in textbooks. So Bernoulli pointed out that this pressure and the velocity relationship is actually giving us the sound which usually you see in musical instruments like in flute. So with all this, can we, make an acoustic frequency spectrum? So acoustic frequency spectrum means usually we see in optics light, electromagnetic spectrum, wave spectrum. So here also we can see in acoustics that there could be an ultrasound frequency spectrum, where ultrasound usually works between 20 kilohertz to 100 kilohertz. So this is sort of power ultrasonics. Of course, we know that so from 20 hertz to 20 kilohertz, this is the audible range, but above that, ultrasound can work. So range of power electronics is 20 to 100 kilohertz. With this in mind, let's study something fun, some very fundamentals. Students will appreciate this. So this is 1D plane wave. As you know, the k and omegas in this, and then if you make it a time derivative, you can get the velocity and accelerations. And then there could be phase shifts, restoring force, and energy density. All these are like BSc first year physics. And then wave equation in solid. So wave equation in solid is actually combining Newton's second law and Hooke's law. So stress strain. So usually this is something to do with the Navier's equation of motion, where mass density of solids, mechanical displacement vector field, and elastic constants and volumetric dilation is introduced. In this case, Helmholtz theorem and longitudinal and transverse waves comes. So how sound propagates? In case of longitudinal waves in solids, which is P waves, compression and rarefaction happens, plus 12 signs. So as you can see, the velocity, longitudinal velocity, depends on shear bulk modulus, shear modulus, and elastic constants. So this is the expression of longitudinal velocity, and due to that, you will have compression or rarefaction. How about transverse wave, which is S wave? This is also familiar to us. The propagation direction is in this direction, and the particle motion is in this direction. So this is transverse motion. So particle oscillates perpendicular to the direction of the wave travel, creating a dynamic shear stress within the solid. Again, this velocity is also dependent on shear modulus and the density. So these are the very important things for sound. You have to know different elastic modulus and density of the material to understand the velocity through the material, the sound velocity. Now, wave velocity relations and material constants. Of course, we all have isotropic elasticity relations. And then if we take some known material and our materials for targeting this approach, as you can see, aluminum is something which is the density, Young's modulus, Poisson's ratio are all known for a long time. And then silicon, that is also known. And then if we target our material, silicon dioxide, because we will be using something like a silicon dioxide platform wafer. So silicon dioxide, as you can see, longitudinal velocity is 5.9 and shear velocity is 3.7. Now, if you consider MOS2, which is our semiconductor, longitudinal velocity is 6.7 and shear velocity is 3.7. Now think about, for students, impedance matching. So if you think about impedance matching, usually electrical or electronic circuits comes into play, right? So the input and output should have a very good impedance matching. So this is also applicable in case of sound, because if we have a good transmission of sound effect, then we will have the basic parameters, material constants should be close. So in that sense, if you consider silicon oxide and MOS2, they are pretty close. To be specific, acoustic impedance you can also calculate, and that is rho into V or C, the sound velocity density. And then you can see that for MOS2, acoustic impedance is not that far from silicon oxide. So that has given us the confidence that if we can create some sound in silicon oxide, silicon wafer, then we would probably can pass through without much attenuation, and MOS2 can be, the semiconductor can be affected. Of course, it's not only a linear propagation, so we can have nonlinear acoustics, so finite amplitude effects, different harmonic generations, shock can be created. So all these can be the sub-product of this effect. For the moment, let's keep ourselves in the linear regime. So ultrasound generation, first idea was piezoelectric transduction. So you can create different interdigital transducer and pass wave from a bulk transducer. Bulk transducer is a piezoelectric one, and you can create acoustic waves. So this is one aspect. Then the second aspect, which is our approach, is vibrating tip, which will produce something like 100 kilohertz sound, and then there will be some target device, so the sound will propagate through. So the wave front will be propagating through like this. This is second. And the third one is the laser induced sound. So you can have pulsed laser beam hitting on a surface, and it will cause localized rapid heating, which will create broadband pulses. So all these have different target applications. We will choose for this experiment mechanical or wire bonding tip. How can you detect this sound propagation? Of course, pulse echo is one aspect which can be used, which is like a reflection. So as you can see here, a single transducer acts as transmitter and receiver. So you create some sound and get the sound, so it's more of an echo. You can create transmissions, so through transmission methods, so dual sided, so you can create and then get the transmission spectra of sound. So it's like two separate transducers on opposite side of the sample, and then time of flight. So we will use this one where we will create sound, and we will see electrically how the time of flight of the sound is affecting our electrical device. So time of flight measurements provide fundamental parameters like wave velocity, thickness, even attenuation and echo amplitude can be calculated. Now coming to the main work of this project, which is acoustic manipulation. From this figure, as you can see very easily, this is a FET. Why it is a FET? Because there is a source and the drain, and then there is a channel through which charge carriers are flowing, and then there is a gate which is like a dielectric and a conductor. So this channel will tune the electrical conduction through this FET. Now this is very known to us, right? FET architecture. Now if we have a ultrasound tip which is hitting the surface, which is carrying this FET, and then the wavefront passes through this, what will be the effect? This is the main question. Now, how will we create this ultrasound? For us, it's very easy. As you can see from this picture, this is our lab picture of the homemade setup. As you can see, this is the ultrasound tip, which is from a wire bonder. Usually, wire bonders are used to create those circuits. I have shown you some wires from big pads to small pads, some wires in the first or second slide. So that is the main source of ultrasound for us, which will produce frequency of 100 kilohertz, pulse duration of 50 milliseconds, power 2.5 watt, and bond force. It's absolutely controllable. So we can control the ultrasound propagation quite efficiently. Now we know that in this small area there is even a smaller circuit which is located like this, the schematic, or this. And then whenever we hit far away, how the ultrasound is affecting this. Again, we will use this impedance matching condition to find the best transmission for our circuit. So for us, we have calculated that transmission efficiency is 83%, which is considerably high. And we will have different reflection from gold MOS2 to create standing wave. I will show you next. So the setup is like this. I have already discussed. This is ultrasound tip heating, and then the propagation of ultrasound, and then this is the circuit. So this is the transfer curve of the transistor, which is gate and the drain current, and you have nonlinear IV, which is at certain gate. So this is set up for acoustic wave propagation in an MOS2 FET with a bonded tip. A schematic of the MOS2 based is here, and we are passing 100 kilohertz ultrasound. Now, layer dependent piezoelectric response of MOS2. Now, MOS2 being a van der Waals system, it is, you can exfoliate and get different layers. In monolayer, it's non-centrosymmetric. So if it is non-centrosymmetric, you can understand, then piezoelectricity can be achieved. But it is, when you get a bilayer MOS2, it's centrosymmetric. So for bilayer MOS2, its piezoelectric response will be off. Now that's a very good point for us, because we can create as we wish different layers. So we can check or confirm our experiment with different layer circuits. So that is what we have done. For monolayer, whenever we hit the surface, we can get the transients, as you can see here, I source drain with time. So we can get the transients, and whenever we have a bilayer MOS2, we get a flat line. So this is coming purely from the monolayer MOS2. Now we know what we are doing, because we can do Raman to check the circuit from where we are measuring. So from the circuit we are measuring, we know that this is the monolayer from Raman and the bilayer. So because monolayer and bilayer, Raman, separation between two characteristic peaks are different. So it's very deterministic. So whenever you are sure with monolayer and bilayer, you create circuits and do the experiment. And then you can tune the gate to see whether it is completely tunable with gate, because the sensitivity depends on the gate. Why? Because whenever you see the off state, when the gate is negative voltage, because MOS2 is a N-type circuit. Whenever you have a negative gate, it's in off state. So you will have no sensitivity, because you cannot hit, you cannot get the peak of from the ultrasound. But whenever you have in the on state, you will get it very efficiently for different heats. So as you can see here, for different circuits, you can sort of tune the gate, you can get the transients, and you can repeatedly hit to understand how the response is getting changed. Now, what about if you change the power of ultrasound? So if you change the ultrasound power, you can see that the drain current increases. If you change the gate voltage, you can see that whenever you hit, there is a dip in this transfer curve. So that can be coordinated. And you can actually simulate this from the experiment. How? So my student did COMSOL to understand these experimental results. So what he did a mesh of on silicon surface and MOS2, and he can create this wave which will propagate through the surface and measure the response. Now, if we place different mirrors, in our case gold electrodes, then as I was mentioning, you can create sound waves and standing waves, and then you can create this transients broader, so you can keep long time this effect of ultrasound. Now that is what actually happens in our experiments also and in theory. So as you can see here, this is the first hit, and then if you have different circuits, as you can see here, multiple circuits, so multiple reflection happens, so you have dips, and simulation also shows the same. You have a broader peak in case of different electrodes. So can you efficiently, deterministically put mirrors and see exactly the same? So this color plot shows our sound engineering in microelectronic chips. This is from a pure calculation, and then we did the experiments where standing waves are only formed inside the circuits. So you will have long time where the sound effects is on. So this is the experiment where you can put your gold mirrors according to your wish, where only standing waves will be passing, will be created. So in short, we have created atomically thin loudspeakers depending on the, of course, the layer thickness. For monolayers, we have, since the broken inversion symmetry will create piezoelectric signal, and for bilayer restored symmetry will give no piezoelectricity. So this is sort of a this will determine why the signal is coming from a specific layer thickness, and then piezotronic mechanism can be understood from the Schottky effect, and the findings are like, this is a probe which will make mechanical to electrical energy harvesting, and then we have calculated the heating process due to this piezo current. So this effect is very high in signal to noise ratio, because you can see the peak to base ratio is more than 10, and it's silicon surface compatible. How much time do I have?
You have more 10 minutes. You can take 10 minutes.
Okay, thank you. So the physics behind this effect is elastodynamics and measurable current. Now, students might find it relatable with their coursework that longitudinal ultrasound wave injected from the tip into SiO2 can be, in our case, can be termed as this. So U0 e to the power I kz minus omega t. How will you find strain? Strain can be found from del U del Z. Why del Z? Because the propagation is Z direction. So you can create along Z direction, let's say, epsilon ZZ, which is del U del Z. How can you find stress? So stress is rho into V square, which is the component. So stress by strain is the elastic constant. So that into strain. So you can create stress relationship from your wave propagation. Now this is through SiO2. You have to understand that this is through SiO2. How can we get transmission to MOS2? Of course, as we have discussed, a stress will be transmitted from SiO2 to MOS2 with a transmission factor, and the transmission factor is 2z by z1 plus z2, and z is rho into v, velocity. So epsilon is the strain is sigma stress by Young's modulus. Now piezoelectric polarization, we know that the E11 component of the strain into epsilon, which is strain. So P is E11 into E. We are only considering this sigma and epsilon, stress and strain. So this is the elastic tensor. So induced piezoelectric field and potential would be this P by epsilon r epsilon 0. Griffith, pure electrostatics, electrodynamics book. So that from this electric field, you can find out voltage, which is E into dr, E dot dr. So which is T. So piezo current can be dp dt. So I polarization will depend on polarization derivative. So the bottom line is ultrasound will create a strain field. Strain field will create a polarization. Polarization is the source of piezoelectricity. Polarization will create a time varying electric field, and that time varying electric field will modulate the current. So breaking of symmetry and the nonlinear transport is governing this physics. With ultrasound of pulse, let's say 10 to 100 millisecond, 100 kilohertz frequency. And the measurement bandwidth is averaged over many cycles. In our case, since we have shown nonlinear plots with Schottky barriers, it acts as a rectifier by forming metal semiconductor junction. So that is why you are seeing this transient in our case. I have mentioned in the application that from our circuit, we can get the idea of how, due to one heating, this piezotronic current can be measured, and this piezotronic current, since we can measure this piezotronic current, so there will be some localized heat because I square R, right? Now this I square R, if you calculate from the strain and the piezoelectricity, we have calculated that it is estimated as 20 Kelvin. So the temperature rise is 20 Kelvin. Now think about it. Now we are trying to connect chemistry to this experiment. We have a microelectronic chip.
Sir, can you?
Yes.
Sir, I request you to conclude in 5 minutes.
Thank you. So we have a circuit, and then sound is propagated. So sound is propagated, and we have measured that the localized temperature rise is 20 Kelvin. So if a catalytic reaction needs 20 Kelvin boosts, you can create this from the circuit current. So it's a microelectronic reactor, because 20 Kelvin rise of temperature, we have observed from the literature that, let's say, H2O2 decomposition, which is considered as a very important reaction for chemists, that needs a 20 Kelvin heat. So in our case, this circuit, this small microelectronic circuit, can be used for catalysis. I would like to conclude with this this slide, that this localized Joule heating in this circuit, it's a prediction. How can we get the realization of this? You need microfluidics, because on that channel, through that channel, there should be some liquid which will be interacted or interfaced with this. It's not easy, because decomposition should be probed. So you need some sort of an FTIR probe. You need some liquid confinement, microelectronic circuits, ultrasound, and device. We are trying this. This is also a homemade microfluidic device, which is placed on a circuit. And we can see that there is a change in the current, but source not yet known. It's a technically very difficult experiment which we are trying to do. I will skip this part and conclude that our experiments show that piezo current can be measured due to ultrasound propagation. A bonded tip, wire bonded tip has been used as a generator of sound. Multiple reflection effects of sound in circuits has been realized, and acoustic manipulation of van der Waals semiconductor device. This is the main objective of this experiment. So in a way, our experiment for the moment actually connects all parts of this two-dimensional physics to acoustics. This project was primarily done by one of our BSMS student in our group, who is in Ohio State for the moment for PhD. So he did this project, Barnick, and duly help from one of my PhD student, Rahul Poromanik. I've been blessed with research funding from DST SCRB and special funding, and I hope that with the current funding from NRF in ARG, we can create a part of the laboratory which will be dedicated to laser Doppler vibrometry, means ultrasound. Thank you very much.
Thank you, Professor Sohail Datta. His talk. Now, talk is open for discussion. Any questions from the audience? Yeah, there is one question.
Hello, sir.
Yes, I can hear you.
Interaction landscape system. So, how do acoustic fields actually control or influence the electron transport in this system?
Oh, yes. I have slides. Yeah. Yes. So, can you see my screen?
Sir, I said like how do acoustic.
Yes, sir, your screen is visible.
Yes. So acoustic field will create a strain. So if you have electron phonon coupling in the system, so as you can see here, this deformation potential will perturb your electronic current. Is that the? I mean,
Okay.
if I answer you correctly, is this the question?
Yes, sir.
Okay. So at the end of the day, see,
Sir,
sound is a
actually,
mechanical wave. It will create lattice strain.
sir,
So
actually, in the
strain.
interaction landscape, actually, there is a interaction between phonons, magnons, and the electrons. So, I
Yes.
just asking like there is a, I guess there is the most important here is the electron transport. So, basically, my question was like acoustic field do actually influence or like on the like larger scale or a smaller scale, like how?
Okay. Now I understand. Okay. So now, my first answer was you understood, right? It's a strain. At the end of the day, sound is a strain effect. So strain effect will perturb your phonons. Of course, it depends on the materials where electron phonon coupling, if you can perturb phonons quite well, then you would be sort of realizing effect in the electron transport. So it absolutely depends on how lattice is coupled to electronic system. From our measurement, I can tell you from electron magnon, which is at the end of the day passing through a lattice. So magnon, from this experiment, we have observed that if you perturb your lattice, then this perturbation will give you a measurable current. Now, and that current is coming from the electron magnon interactions. So to give you this idea, if you see this is the magnetoresistance and this is the magnetic field. So if you create strain, this magnetoresistance will be changed. And that is the experiment which we want to do with the magnets.
Okay, thank you, sir.
So any more question from the audience? Yeah, there is one more question, sir.
Good morning, sir.
Yes.
So you mentioned the term microfluidics. So I want to know about that. Like, can it help in detecting diseases? If yes, how?
Oh yes. I'm not an expert in diseases detection, but I have seen many papers where detection of, I mean, bio application of microfluidics. People are working on it. If I go back to the slide, if I may, yes. So I give you an impromptu answer for this. Let's say this one. Okay. I think you can see my video, right? So, so let's say in this case, this is something. If I remember well, we have passed sugar solution and water. Sugar solution and water. Sugar solution is coated with some dye so that we can understand, we can pass different liquids together. Now, think about minute detection of undesirable ions in your in your flow which is going through your body, in your body. Can we detect that in microfluidics? Because this is in the picoliter regime. We have calculated this volume. We can get picoliter volume of liquid. Now, if we get a picoliter volume liquid with a controllable flow, let's say this is something which is injected to your body, and you do not want a specific element or compound in your system, then that small amount, let's say picomolar or attomolar, I don't know, that can be sort of detected. But that is a very impromptu answer because I am not an expert in bioscience, but I have seen few papers where microfluidics are used for detection of undesirable elements or compounds in biofluids.
Okay, thank you, sir.
So, so maybe Dr. Haryana, if you have any question, okay. So if there is no question, then let's thank Dr. Datta. Thank you, Dr. Datta, for joining us for this session. Thank you so much.
Thank you. Thank you very much. Thank you very much.
So now we proceed for the third talk of this morning. And we have with us Dr. Umesh Kumar Dwivedi, who is presently working as Associate Professor and Coordinator of Applied Physics at Amity School of Applied Sciences, Amity University, Rajasthan, Jaipur. He completed his PhD from CSIR Advanced Material and Processes Research Institute, AMPRI, Bhopal in 2008, supported by a CSIR Senior Research Fellowship. His areas of expertise include nanocomposites, tribology, functionally gradient composites, EMI shielding, and electrical characterization. Dr. Dwivedi has published over 125 publications in national and international journals of repute and 15 book chapters, including authored books on tribology of NFRP composites and analog electronics. He has guided 15 PhD scholars and 25 master thesis students, with 6 PhD scholars currently in progress. His H index is 25 and I-10 index is 45, with over 2,325 citations at the international level. He has received the Best Research Paper Award in SCI journals from CSIR AMPRI and the Best Researcher Paper Award in Rajbhasha from CSIR. So he will talk today on the topic development of polymer composites and their applications. So Dr. Dwivedi, I invite you for the talk. So you will have 30 minutes.
Good morning. Thank you. First, I want to thank organizing team for inviting me for giving my presentation in front of you. And thank you, chairman of this session also, Dr. Vij. My topic is polymer composite and their applications. Present scenario is seeking the best substitution in the field of materials. Everybody is changing the material day by day. Initially, metallic composites were used, now polymer composites. So change is there. But parameters, what parameters are there? Scientists consider that material should be eco-friendly, higher specific properties, cost effectiveness, and better performance. By these parameters, there is a huge demand of composite materials nowadays in every sectors where we will go in automotive, construction, medical, electrical, electronic, security, aerospace, everywhere. Now composite materials are used. So first, what is composites? Composite is a combination of two or more materials which are immiscible in each other and are separated by the interface. That is the proper definition of composite. If it is miscible, then it is not composite. Then it is known as blend. Or if metal matrix is there, then we can say it is alloy. So we can say a solid mixture bind together their constituents is known as composites. So there are basically three types of composite material: metal matrix composite, ceramic matrix composite, polymer matrix composite. We will go in polymer matrix composites. So according to different parameters, these are the classifications of composite materials. In continuous phase, if polymer metal is there, ceramic is there. If polymer, then thermoset, elastomer, thermoplastic. So these all are the category of composite materials. Polymer, it is already known that a large molecule composed of repeating structural units connected by covalent chemical bonds are known as polymer. So there are different type of polymers. We generally say is that engineering polymers have three category: thermoplastic, thermoset, and elastomer. Thermoplastic, which are if we supply thermal heat, then we can redesign, we can reshape it. But in thermoset, once it is set, you cannot do anything. It is set, you cannot change the structure. And in elastomer, it has elastic properties. So these all are the examples of thermosets: epoxy, polyester, phenolic, thermoplastic like polyethylene, polypropylene, polycarbonate, polystyrene, PET, PVC. These all are the example of thermoplastic. Elastomer like silicone, neoprene, polyurethane, etc. All are the examples. So we introduce fiber. Fiber, there are different type of fiber, natural and synthetic one. So we can categorize like in this way: non-wood and wood fibers. So these all are the examples: sisal, coir, cotton, bamboo. These all comes under the category of natural fiber. And synthetic fiber, glass fiber, carbon, Kevlar, graphite. These all are the synthetic fibers. You can see here natural fiber, and in downward it is synthetic fibers. You can see this is the woven, roving, random mat, woven fabric, carbon fiber, and woven fabric. Black one is carbon fiber, and white one is glass fiber. So this is the methodology by which we produce composite materials. So what is the role of reinforcement? Reinforcement is the principal load bearing member in composite material. And what is the matrix? It provides medium for binding and holding the reinforcement together into a solid. It protects the reinforcement from environmental degradation. It serves to transfer load from one insert to other. So these are the main function of reinforcement and matrix. You can see there are these are the variables by which, if we change these variables, output will be changed. So we can design composite material as per our requirement by varying amount of percent, amount, weight percent, fiber length, distribution, orientations. By these, we can change the properties of composite materials. This is the beauty of composite material. If we need high strength, low strength, so we can change. These all are the variables. You can see here, like tensile strength in the same composite material. If it is 90-degree parallel, then the tensile strength is around 100, and 4 times it is increasing if orientation is changed. So there are different applications of polymer composites in every sector. Polymer composites are used nowadays. After computer technology, IT, we can say composite technology is used nowadays. Applications in aerospace, automotive, construction, medical devices. You can see here in composite in Boeing body, composite parts, around 50% composite parts are used. You can see in railway, a chemical tank, electrical switches, these pillars, FRP gearbox, these all are made up of composite materials. And earlier it was used, made by metallic materials. Now it is made by fiber composites. Here you can see new generation of LPG cylinder. It is already in market. Go Gas is supplying this cylinder, and that heavy cylinder is now being replaced by this polymer composite materials. It is a seamless composite translucent cylinder made up from a polyethylene molded inner lining, glass fiber, and resin with inner liner to create an even greater strength, and an outer layer makes this a perfect one to use. So this is already in market. So you can see how the technology is being shifted here. Now metallic cylinder is replaced by fiber composites material. You can see glass fiber Sharia. It is in construction. It is 30% cheaper, 9 times lighter, 3 times stronger, and 0% corrosion. 0% corrosion is there. Earlier, that metallic Sharia has corrosion problem. Now it is being replaced by using composite materials. Like FRP shelter. FRP shelter, if you want to make any shelter in a higher altitude, then it is very lightweight and it is reassembled. And you can easily take this with a small area, and you can construct easily. In automotive industry, around 40%, 50% composite materials are used. In polymer composite, gas barrier properties also there. So nano composites creating more tortuous path for gas molecules. So it is also being applicable in packaging, food packaging like soda bottle. It is used. Polyurethane nano composites are used here in medical applications, in LTA system, hot air balloon. This type of polymer composites are used. Automotive tire application and coating, this is also there. In EMI shielding, nowadays everywhere radio signal is there. So radio signal is there, so EMI shielding will affect the performance of components. Hence, EMI shielding is required. So now, flexible electronics, this type of EMI shielding nano composites material are used. We have already developed some nano composites by using CCTO and cobalt ferrite with elastomer for ISRO project. So this all are the disadvantage of EMI shielding. You can see these waveguide gasket, flat washers, these all are made up of polymer composites, elastomer polymer composites. And it has property of absorbing microwave. In tribology means where friction lubrication comes under the category that is known as tribology. So most of the components are replaced by polymers because it has self-lubricating property. So these all are the components made up of polymer composites instead of metallic composites. But some limitations are also there. Limitation, what are the limitations? Low maximum working temperature, sensitivity to radiation and moisture. Processing temperature are generally higher than those with thermosets. Required special processing equipment. For different polymer, we require different type of processing. That is one of the disadvantage in this area. Thermoset resins have poor impact resistance, so we should increase, then we can use it. So now polymer processing. There are different type of polymer processing: hand layup, resin transfer molding, pultrusion, filament binding, injection molding, extrusion, air blowing. It is in thermoplastic, and upper one is in thermoset. We use different processing techniques. Like pultrusion here, it is the process where composite parts are manufactured by pulling layers of fibers, fabrics bathed with resin through a heated die, thus forming the desired cross-sectional shape with no length limitation. By using this, we can make different type of pipes, and saria is also made by using this technology. In RTM, we prepare different type of components, structural materials. So that is the process of RTM, where preform is made, then tool is insert into the mold, and injection takes place, where resin, we insert resin by using pressure, and after that curing takes place, and we demolded that component, by which we make this type of heavy components by using this type of processing. In injection molding, we use generally use this technology for making thermoplastic material, where pellets are kept in a hopper, and a screw will take place, and heater, different zone of heaters is there. So thermoplastic materials will melt and push into the mold. Then we prepare the different type of components. It has advantage like process can be fully automated, high productivity, quality, price is very low. So these all are the processing. One special material, that is functionally gradient material. It is functionally gradient material is a heterogeneous revolutionary material that belongs to the class of advanced engineering material. It has different compositions with the thickness. So this is one of the good, we can say good technology if it is used in daily life. Because FGM exists in the nature and in the human body as teeth, bones, wood, and bamboo. You can see here, FGM is there. Our bone has this structure, functionally gradient structure. This provides a smooth transition for stress. That's why very less damage is taking place. In bamboo, it is also there. You can see in outermost cellulosic fiber is more, and in inner side cellulosic fiber is less. So it is gradually changes. So it has very good property. We can utilize this technology for making different smart materials. So it has a smooth transition, improved adhesion, effective thermal stress relaxation, high surface wear resistance, high toughness, stiffness, better flexural stance. These all are the special property of this material. Applications area in biomedical engineering, defense, coating, everywhere we can use this technology. And various processing approaches are there. Chemical vapor deposition, plasma spraying, centrifugal casting, thermal chemical reaction. So powder metallurgy, these all are the different processing by which we can make a functionally gradient material. So why gradient material? Functionally gradient material comprises lower volume percent of fiber, whereas conventional composite comprise of higher volume percent. Hence FGM is cost effective. In suppose if we are adding only 3%, so with 3% we can achieve the property of 40% fiber by making gradient composite. So surface will be more resistant as compared to inner one. If we want to use high wear resistance at only surface, unnecessary why we are incorporating costly fiber throughout the matrix. So we can use this technology to reduce the cost also. We have already developed this centrifugal casting machine in our laboratory, and we have published around 20-30 papers in this area, and we found that we have good we are achieving good properties. Like you can see here, pure epoxy has this amount of wear, but if we centrifuge it, it comes under it is 30 minutes centrifuge, then we can reduce it around 4 times. So it is very good. Even coefficient of friction is also changed. So these all are the properties. Like here in this paper we have developed functionally gradient material. One surface is conducting and another surface is non-conducting. So same material is behaving in two ways. Upper surface is conducting and down surface is non-conducting by making gradient distribution. So these all are the papers which we have already published. So you can see the gradual changes is there. Gradual changes is there. This is UHMWPE functionally gradient material. Upper surface is highly wear resistant, and bottom surface is has a very low wear resistance. So this type of composites we can make by using functionally gradient materials. So we have already discussed it. So this technology of making FGM still remains in the experimental stage because of the lack of information on fundamental understanding of transport phenomena occurring in a dispersion under gravitational or centrifugal force, particularly in a matrix which changes its characteristic with elapsed time. For example, polymerizing fluid. So that's why it is not at industry level. It is in research level. So now the application is tribology. Tribology, it is a silent killer of components. We can say around 60% losses of industries because of only tribology. Because it is the synonym of with reliability, long life and energy saving. It is one of the most and thrust area in the science and technology because industrial loss because of the components failure or component failure is only because of the tribology. Different type of wear is taking place. Sliding wear, abrasive wear, fretting wear, fatigue wear. So these all are the challenges which is we can say it is the thrust area of DST also. Despite of its importance, research related to friction and wear has not received sufficient support in the past because this is a very complex process. It involves very different parameters which is involved in this process. You can see here this type of components have this type of mechanism in tribo system. These all are the failure because of the tribology. Wear is taking place. So we have to reduce it. It is the challenge for scientists, material scientists, how we can develop this type of material which has no wear. In human related tribology, teeth, bone, every part that is, if it is with the age, it is replaced because of the tribology. So similarly, we can make biomedical applications, valve, hip joints, knee, pump components, we can make. So ultimately, there are the remarkable points. Interface plays a dominant role in composite. Fibers, nanofillers distribution drastically affects the property of composite. Moisture of filler or fiber is providing poor adhesion. Moisture is playing very important role in polymer composites. I have worked in industry for some times and I found this is the biggest problem. in making polymer composites. If moisture is there, then interface will not take place. Your strength will lose. And that is the biggest challenge, how to remove water content at the surface, because you are joining two surface, and if water is there, water cannot retain any other material if moisture is there. So moisture is very important if you are making polymer composite. First, you should remove properly moisture, then only you can make a good uh, polymer composite. We can play with the process and subsequently with interface, orientation of fiber, dispersion of filler to get desired material property. We can play all these parameters and we can make desired material as you want. So this is the beauty of composite material. And we can play with polymer composite because it has, we can say it has a lower cost. And in room temperature, in laboratory, we can make this type of polymer composites easily. Because metal matrix composite and ceramic matrix composite required high temperature, around 1000, 1200 temperature is required. But for polymer composite, it is not needed. It is, we can make in room temperature also. So this is a good property of this polymer composite. So how do we modify the composite? By changing filler fiber or matrix, by changing the manufacturing process, by changing interface by chemical physical treatment like irradiation, coupling agent, heat treatment, plasma treatment, and other also. So we can play all these things and we can get desired property. So what is the conclusion? From automobile to aerospace, medical, military technology, and even in a household, day by day, the field of composite material is getting stronger. Among all the composites, polymer composites have a strong place due to its specialization. In Amity University, Rajasthan, we have some research facility like FESEM, we have LCR meter, gas sensing unit, high temperature furnace, all these things we have. And these all are my PhD scholars. We have already completed 15 PhD scholars to award PhD. Thank you.
So thank you, Dr. Dwivedi, for a very wonderful talk and insights on the polymer-based applications, polymer nanocomposite, how do they play a very vital role in our day-to-day life. So now we can take few questions from the audience.
Morning, sir.
Yeah,
Sir, I want to ask that still in the industries of aerospace and in space, still we use only 50% of composite materials to make aircraft bodies. Even the latest aircraft, that is A350, uses 50% composite material and still relies on metallic alloys and the titanium. So how do you think that we can achieve to, because we are composites are dominating the metals because they are light. So how do you think that we can make the aircrafts more efficient? Because engines are somewhere getting more efficient, but aircraft bodies are still lagging behind because of the less use of composite materials.
Yeah, composite material, it is, research is going on. And there we are using some metallic material because temperature is also a problem. Because at a higher altitude, low temperature is there. So low temperature has a disadvantage that in composite crack may take place. So that's why it is in not everywhere it is used. Some parts that is possible that we are making. So it is the part of research. Maybe after sometimes every part is made up of only composite.
Like the recently Artemis 2 mission took place, and it was still. I mean, it feels strange that it was still using this part of space shuttle program from 1980s, and we have technological advancement in these 40 years, but still we are using those materials from the special programs. How can we use composites to use, efficiently use uh, those composite materials to make these space missions more efficient?
We can simply say कि आवश्यकता ही आविष्कार की जननी. If need is there, definitely research will take place. जैसा जैसा आवश्यकता पड़ेगी, we will go with this material. If it is not needed, if work is going on with the raw material, then unnecessary, no need to replace that material until it is costly or it has some other disadvantage like environmental issues, cost. If these are there, then obviously researcher will do this thing.
And also, I would like to add to this that it takes years for any research outcome to put into practical applications. So maybe in research labs it is there, but it will take some time. It will be tested rigorously before it is put into applications, real world application.
Yeah, I want to say that that cylinder that I have shown here, it has taken around 10 years to make to come into the market. In 10 years research, that is the outcome. When we are doing PhD at this time, this work has started.
So any more question?
Yes, sir.
Yes, there's one more question.
Firstly, thank you for your insightful talk. I would like to ask, what are the key challenges in replacing LPG steel cylinder with composite cylinders, particularly regarding durability and cost effectiveness?
No, it is already being replaced nowadays.
So, but in the terms of cost effectiveness,
It is cost effective. It is cost effective.
does it is cheaper than other steel cylinders?
Yes, yes. That depends on the production. If production will more, definitely cost will reduce.
Thank you, sir.
So there are plenty of questions, I think.
गुड मॉर्निंग सर.
They are taking interest.
That's good to know.
सर आपने अभी बोला कि
आवश्यकता आविष्कार की जननी है.
आविष्कार की जननी है.
हाँ.
सो अभी मेन आवश्यकता तो यही है ना कि हमको सरवाइव करना है अर्थ पे. इतना टेम्परेचर है, इतना पोल्यूशन है, इतना इन्वायरमेंटल फैक्टर इफेक्ट्स है और हमको सरवाइव करना है. और जो आपने बताया थर्मोप्लास्टिक एंड प्लास्टिक, ये तो कभी बायोडिग्रेड होंगे ही नहीं हमारे. सो इज देयर एनी वे?
पहले पॉलीथीन जो आती थी वो बायोडिग्रेडेबल नहीं थी. आज आप जो पॉलीथीन ले रहे हैं डी मार्ट में, रिलायंस में, दैट इज बायोडिग्रेडेबल.
सर बट कितने टाइम तक? लाइक
क्या?
इट आल्सो रिक्वायर्स सम टाइम ना. बट कैन बी से कि हम कुछ ऐसा निकाले कि वो जल्दी बायोडिग्रेड हो जाए?
यदि बायोडिग्रेड जल्दी हो जाएगा तो आपको मैं कहूँ कि वहां पर कुछ गीली चीज लेकर के आनी है तो वो तो वहीं डिग्रेड हो जाएगा.
सर
उसमें
वही तो आवश्यकता हो गई ना फिर हमारी.
नहीं, आवश्यकता नहीं. इट डिपेंड्स ऑन द एप्लीकेशन. यू रिक्वायर्ड हाई स्ट्रेंथ आल्सो. यदि इतना आप उसका पुअर वो रखेंगे कि वो वाटर डालते से ही बायोडिग्रेड होना चालू हो जाए, तो फिर आप क्या उसमें कुछ सामान रख पाएंगे?
बट सर इफ नीड इज देयर कि हमको पानी डाल के खराब नहीं करना है, बट वी आल्सो रिक्वायर हायर स्ट्रेंथ ऑफ
देन
मटेरियल.
यू कैन गो विथ पेपर बैग.
बट दैट
बट
आल्सो
पेपर बैग कैन नॉट डू एवरीथिंग. अब सपोज पीवीसी पाइप है. पीवीसी पाइप आजकल सारे वो लोहे के पाइप हट गए. ठीक है. अब लोहे के पाइप में प्रॉब्लम क्या थी? करोजन. अब करोजन सबसे बड़ी प्रॉब्लम, उसको केवल हटा सकता है पॉलीमर. अब वो पॉलीमर का आप आ गए. अब आप चाहो कि नहीं वो भी बायोडिग्रेडेबल हो जाए, तो फिर वो बायोडिग्रेडेबल हम अंडरग्राउंड जब उसको लगा रहे हैं वो बायोडिग्रेडेबल हो जाएगा तो क्या हम उसका यूज कर पाएंगे?
सर जो हम पॉलिथीन्स की बात करी, या पॉलिथीन्स जो आपने अभी बात करी, या फिर कुछ टॉयज हो गए बच्चों के, या XYZ हमारे पास ये माइक भी हो गया, अब ये खराब हो जाएगा. दो इट इज नॉट मेड ऑफ
थर्मोप्लास्टिक्स आर रिसाइक्लेबल. ये अवेयरनेस सभी को है आजकल कि ये रिसाइक्लेबल है, इसमें कोई इशू नहीं है.
एंड सर दोज
इसमें आप डिग्रेड करने की बात कर रहे हैं, आप उसको रिसाइकल करो ना. आप उसको रिसाइकल करके प्रॉपर जगह और उसे रिसाइकल.
श्योर सर.
Right. So there was one more question from the girl student.
Good morning, sir. Sir, in one slide, you discuss about the graph between tensile strength and angle between fibers and stress. So, there was a statement that maximum strength is obtained when long fibers are oriented parallel to the applied load. So, I just want to know about what is the behavior at different angles like 0 degree, 45 degree, 90 degree, and why parallel is having the maximum
This
strength.
property is known as anisotropic behavior.
Okay.
Anisotropic behavior. Like bamboo. यदि बैम्बू है तो बैम्बू को आप इस तरीके से यदि आप उसे तोड़ना चाहेंगे ना तो ये नहीं टूटेगा।
Yeah.
लेकिन आप ऐसे तोड़ेंगे तो टूट जाएगा। आप बिस्किट, पार्ले जी के बिस्किट है सपोज, आप बिस्किट को ऐसे रख करके खड़ा उसे रखेंगे ना तो आप उसको ज्यादा प्रेशर लगा, और यदि आप उसको ऐसे रख करके और करेंगे तो कम लेगा। इसे इसे हम कहते हैं एनाइसोट्रोपिक बिहेवियर, और ये होता है मॉलिक्यूल अरेंजमेंट के कारण। वहां पर जो मॉलिक्यूलर अरेंजमेंट होता है यदि वो डायरेक्शनल डिपेंडेंट हो जाता है तब ये प्रॉपर्टी आती है।
Okay. Thank you, sir.
So, if there is no more question, we thank Dr. Dwivedi for such an insightful talk and very likely interactive session. Students have interacted really well in this talk. So, thank you so much, sir, for being here. So, please stay here with us for felicitation.
Now, I would like to request the session chair, Professor Ankush and Professor Preeti Thakur, to please felicitate our guest.
So we proceed further for the fourth talk of this morning session. And we now make a transition from the beautiful complex world of soft matter and liquid crystals, a domain that dances between the liquid and the solid. So we have with us Professor Gautam Singh, who is presently working as a professor in the Department of Applied Physics at the Amity Institute of Applied Sciences, Amity University, Uttar Pradesh, Noida. Professor Singh earned his PhD from IIT Delhi in 2011 and went on to complete his postdoctoral research at Kent State University, Ohio from 2011 to 2016, one of the premier centers for liquid crystal research in the world. He was also recognized as a young Indian researcher by the University of Politecnica, Delle Marche, Ancona, Italy in 2008. His research interests span soft materials, liquid crystals, polymers, nanomaterials, nanocomposites, synchrotron X-ray scattering, and photonics. He has to his credit 86 research publications, including high-impact articles like Materials Today, JACS, and reports on progress in physics. His H index stands at 29 as per Google Scholar, with over 2,500 citations. And he's also an editor of Molecular Crystal and Liquid Crystals, Taylor and Frankis, UK, and a review editor of Frontiers of Physics. His achievements include the ILCS Silver Medal, 2025 IOP Outstanding Reviewer Award 2025, Top IOP 1% Citation Award 2025, and Dr. D.S. Kothari Postdoctoral Fellowship. So he will be presenting his talk on carbon dots induced vertical alignment of pneumatic liquid crystal for advanced sensing and electro-optical devices. So may I take this opportunity to invite Dr. Gautam. Thank you, sir. The stage is yours. Yeah. Hello. Yeah, it's busy. So you will have 30 minutes, sir.
Yeah. Going there. I was wondering ki. Oh,
Is it a PDF?
no, it's a slide. It should go.
Oh, no.
Okay, so I need to. Okay, that will get. Okay, yeah. So very good morning to one and all present here. First of all, I would like to thank to the session chair, Professor Veej, for a very nice introduction. And at the outset, I would like to thank to the organizer to give me an opportunity to present my work that I've been doing since the past 5 years with my PhD scholar. As the session chair already defined what are liquid crystals, so he made my life a little easier for today. He said it's something dancing and all that kind of thing. So as he said, that is a soft matter. So basically, today we are living in the age of information. And so to present information, we need some display. So I hope you all are aware that these are used, they're not an LCD, right? So in that display devices, people use the material, they are known as liquid crystal material. Now this has been in the market for a long time, but there are certain drawbacks in those devices. To improve on the performance of devices, people started working on the using of the different nanomaterials such as quantum dots and so on and so forth. So today in this talk, I'm going to tell you about the application or the use of the carbon dots as a dopant to this LC matrix and make a composite and understand how the properties are changed, whether they are good or bad in terms of the application. Before my talk, Professor Dwivedi has explained a very good way that what are the composites. So I believe this is going to be example for all of you that what are the composites other system also. So let me go on further. So my talk includes the introduction and then carbon dots of the composites. Then I present my results and discussion and summary, and finally will acknowledge. So let me quickly go through once more what are liquid crystals. We actually all the time when we start our education in the very beginning in this like class 10th or even below than that, we are always educated by that any matter usually exists in 3 states like solid, liquid and gas. Now what is liquid crystal? If I want to explain to all of you, it's a kind of state of matter which lies between the crystalline solids and isotropic liquid. So it has to borrow 2 things. Number one, something like it's sharing some properties from solids and some from the liquid phase and make it liquid crystals. So why they are so useful and why they're so important? It's because they are having this flow nature, they can flow, but same time they will maintain some kind of order, and that order is known as orientational order. And because they are fluid in nature, so we need to, they are very sensitive to surfaces, temperature, electric field, magnetic field, optical field. So what happens basically, we can tune that orientation of this director as optical axis by applying very small voltage, and we can have a device which is very fast switching. So here we can see that on the screen, see the history that how things have been developed here, or it started from 1888 and so on and so forth. On the right panel, I can show you this is one of the recent application of these components. This is called the switchable windows. It's a very useful because we are sitting in your office and you have windows, they're transparent and you don't need to just go and switch off the curtain on. So just we have windows, they are, you can switch it, apply certain voltage, switch the button on, it will becomes opaque. You want to change, so you can change the temperature. Suppose you can apply the field, electric field, you can, suppose outside of the office, suddenly temperature goes up. This window automatically will be controlling your, state of the this transparency. Now, when we come to the point that which kind of material we are going to use or using in these devices. So first one is this called the pneumatic liquid crystal. This is going to be one of the simplest phase of the liquid crystal material. In this, you can see here, there's just my diagram over there. All these are actually the molecules. I mean, these are the schematic. This is like rod-shaped molecules. So what we find here basically that they are the this is like a rod-like molecules. This long axis of the molecule. You can draw a line here and find out what is the long axis of the molecule, and then what we see that on an average, all the molecules will try to orient along a common direction. That is called the director. All right. And this director, which is called, we call it N, that can be switched with the help of this can go from here to can come back this and go back there by simply applying very small voltage or magnetic field as well. So next, suppose this is going to be, let's say, liquid phase, then you come to pneumatic. Then again, if you go further down, what happens? Viscosity increases. Then what happens? You will increase the ordering in the material. This is called the layering structure. So we call it symmetric liquid crystals, where we will have one more additional order that is coming in the structure due to the layer formation. So we have basically there are two different phases. Number one, this is called symmetric A and symmetric C phase. These are the two simplest phases under this category. What we can see here, this is one layer, second layer, third layer, like that. So to define this structure, basically what we have to do, we have to define number one, this is called layer normal K, this is called director N. Now what we can see here, these two are collinear. Means there is no angle between these two, so it's called symmetric A. Symmetric C, what happens? The K remains the same. This director N is going to tilt by certain angle. This is called theta, tilt angle theta. So this is how we can define the symmetric and symmetric C phases. Now this is the main part of the story for today talk. This is called alignment of liquid crystal. This is one of the key parameter whenever we talk about the device based on liquid crystal materials, because without alignment they are not useful. So what are those alignment basically? How to achieve them? There are three categories. Number one, as you can see in the left panel, figure number A. Here this is called the planar alignment. These two are the substrate, including glass, and then you have indium peroxide. Then basically we have to actually use certain kind of a layer. Means it's going to be a polyimide kind of stuff. So polyimide has to be coated on the substrate. You have to do certain processing, and then you rub it. So what happens when you rub that direction? So basically what happens? You will create certain grooves in this surface. And when you fill the materials, what happens? All the molecules will try to align along that direction. So in a nutshell, we can say that in the planar alignment, the director N is lying in the plane of the substrate. Now again, when you go to second part, this is called vertical. In this case, what happens? We have to treat these two substrate by certain alignment layer. Let's say silane. Then that will align this director N vertical to the plate. It's called homeotropic or vertical alignment. Now, the next one is called hybrid. In this case, what happens? In the one substrate, in the, let's say, top one, I'm using the planar anchoring substrate. In the bottom one, I'm using this vertical anchoring substrate. When you fill the material, you can see the hybrid structure, that you will have a mixture of these two alignment. Now, depending upon our requirement of the display or other devices, we have to pick up the alignment condition, and we move on further. Now let's come to this part. This is called carbon dots. So what are the carbon dots actually? They are basically the nanoparticles. They're lying in the size in the range of 2 to 10 nanometer. And why they are so important in terms of others quantum dots? Basically, they have this property of showing this fluorescence that we can control by the size and surface centralization, or we can change these methods. And they are very useful for the bioimaging, sensing, and operating devices applications. Now, where is why we have selected these dots in our work? What is the catch point from there? So when we're looking at the literature, what we found that these nanoparticles have the property that they are very excellent soluble in the water and other organic solvents, and which enhances their use in the. So we have taken this actually property from their behavior and try to include in liquid crystal materials. Now let me show you. So then afterwards, when we move on further, we did little more search on that, and what we found that long back in I think 2015, someone from the USA, somebody from there, they perform experiment and they have used these carbon dots in a sample so-called LC1, where we have symmetric A and pneumatic. I explained to you in the beginning what is pneumatic and what is symmetric A. They dope these carbon dots, and what they told that they went to very high concentration, like 2.58% to 58%. This is very high like concentration to dope in the LC matrix. And so what they found basically that even then they had used the sample cell which has a planar anchoring, means the molecules has to be aligned in the plane substrate. But when they started including these carbon dots, what they found that when they reached to this concentration, like more than 2.5 and less than 5.0. Under that, what they found that in the pneumatic phase, the alignment was changed from the planar to vertical. So that was a novel thing at that moment of time. But then they had a problem that whatever finding they have shown in the pneumatic phase, that was not stable, and as they heated sample to up, that was distorted. And in fact, they didn't talk about symmetric A. What happened to symmetric A phase? So that was the one more point to look into these kind of materials. So now, this is a slide where I want to tell you that what are the materials that we had used in terms of liquid film materials, what are the carbon dots. You can see here on the top, the left side, there is one compound known as 4-cyano 4-pentyl biphenyl. It's called 5-CB. You can see the structure. It's a biphenyl compound, cyano group there, alkyl chain there, and this compound only shows the pneumatic phase, starting from 25 to 35 in this pneumatic phase. When you come to second compound, it's called 8-CB. Here, what you can see that this compound shows both phases, pneumatic and symmetric A. So we can explore these two together. And the next compound, so-called MBBA, is again another compound. This is also showing the pneumatic phase in the from this range given to here. Now on the left side at the bottom, you can see here, this is called carbon dot. This is schematic diagram. What we have in this structure, you can feel that this is core of the carbon dot, and this circle, what I saw, this is something there, and then this is alkyl chain, and this is the groups OH, COH, and phenylpyridine groups are there, which are very much important while they make this compound. Let me pause here. These carbon dots were made by our collaborator, Sandeep Kumar sir from Raman, Bangalore. Now currently he is working at the Sarda University, Greater Noida as a professor. So now how to prepare, how to actually include these carbon dots in this method. What is the method? So there is a very common method over here. I'm not going to detail, but just this is a process that how one can use these carbon dots and make a composite. So it's a simple process that one can go through, and we can actually have these composites. Now the question comes here. Once we have prepared all these composites and we know the concentration, what are the techniques that one should use to check the property change or what happens to there? Point number one, whenever we work on liquid crystal field, this is going to be the one of the material which shows anisotropic properties. So the first thing, if you want to really look at the the structure or something like that, like what happens to alignment, we need to go to use the optical Polargy macroscope. This is a very simple instrument everybody has in their laboratory. This is called optical Polargy macroscope. So that will give you the picture and can tell you that the sample state, whether planar, vertical, hybrid, and whatnot. So here I'm going to show you the result. The first composite is called carbon. CD means carbon dot. Then 5-CB means LC composite. This 5-CB has only pneumatic phase. You can see this phase sequence right over here. So I am showing in this slide. Actually, this is a couple of pictures from A to H. They are called the optical texture. They are images taken by the cross-polarized optical microscopy at certain magnification, and they are taken at temperature 26 temperature. And I want to focus here that all these samples where this image have been taken, this is at the planar anchoring, means the molecules are supposed to align along the substrate. Now you can see on the left figure number A, when there is no doping of these carbon dots, you can see a very colorful and uniform aligned texture, yellowish color. This tells that the sample was aligned as is supposed to be planar because of the rubbing process. Now when you start increasing this, doping this, let's say 0.03%, what happens? Nothing can be seen, but only you can see some colors change slightly happening over there. Then 0.18%, color more change. You can see at 0.25, something more happened. The texture start distorted. Now this is the concentration where these carbon dots actually are trying to overcome that anchoring force given by the anchored substrate to the molecules. All right. Now when you move further up, you can see when you go to 0.3%, everything what you see very visible stuff becomes turned black. Why it looks black? Because this sample is kept under the cross polarizer. Now this time, your N is parallel to another polarizer. This is going to show you the dark state. Now this is called vertical alignment. Now what we can see from here, that these carbon dots are able to change the orientation of the molecule from the planar to vertical without applying any field. It's simply the job of carbon dots, very small concentration. So we went on up to the 100%. So this is a preliminary confirmation that we did from the optical microscopy. After that, just to confirm once more that what we see here is correct, people have to go and do this is called the electro-optical transmission method. Here what we do is the same experiment, only we have to put the sample under cast polarizer. You shine a light, laser light, single monochromatic light source, and then record the intensity of transmission and then plot the graph with the voltage. What we find, you can see this is a graph very on the X you have applied voltage in the volt. This is called the optical transmission. You can plot it here. Now this black point is called pure. What we see, this is you can see there is a certain way of the graph, like goes here and this is a very typical EO graph obtained for the planar nematic sample cell. Now you can see from the graph that what happens when you go on increasing the concentration. You can see we reach to 0.3 weight percent. So 0.3 weight percent, 0.5 and 1 weight percent. They are all lying touching the zero, means the intensity becomes almost zero. Why? Because there's no light intensity getting passed through the cross polarizer. So this is again confirming that the sample is changed to the vertical state because of the carbon dots, like that. All right. So and then of course now the question comes here. We tested this at 26 temperature. What happens to high temperature? People always worry कि कोई अगर डिवाइस बना के रखते हैं यहाँ पे और बोले कि ठीक है यहाँ पे 28 में सब सही चल रहा है, suddenly temperature goes 45. What happens? Will it work or not? So we have to test it. This is called the stability of the device. Now here, as we know that this sample has nematic phase until 35, so we have heated the sample, all these samples where we get this vertical alignment, and what we found that all these three composites where we have vertical alignment remains stable throughout the nematic phase. So that was one of the very good point about all these mixtures. Second point. Now what I have shown you, that is basically this technique gives you the macroscopic information only, the bulk. But when if you want to understand in terms of molecular dynamics, you have to use another technique. This is called the dielectric spectroscopy. I hope you are aware about this technique. By that, what basically we can do, we can simply have a sample cell, we can plug into a CR meter, you set the frequency range, apply certain excitation voltage, and then you scan the sample and fix temperature. So what you get basically, you will get this kind of graph here. Graph number A. What I plotted here basically, on the X you have the frequency starting from 100 Hertz up to go to let's say 1 megahertz, and on the Y-axis you have dielectric constant. I hope you are aware that what is the dielectric constant means. It's simply ratio of the capacitance of material divided by capacitance of air. सबको पता है, I'm talking about the students. They all know how to get this permittivity. Now you can think about it. In this graph, if you look at the graph for 5 CB, the black one is here. So what we can infer from there, in this case, the permittivity is around 6.5 or something like that. Now you go to this composite when the sample went to the homotropic. You can see that 0.3, 0.5 and 1. In fact, these blue lines also 0.1, 0.2, they are also standing up. Means the molecules are trying to go to vertical state. Once they reach, they will they are shooting up to the value of let's say 18, 19. This also tells you that the sample has gone to the vertical state. And this is giving based on the molecular information. Now again, we can apply the voltage to test that. Suppose sample which is planar, what happens by voltage? So what happens at this 0 volt pure 5 CB, you can see the black line here, that black line goes up to there, reaching 18 to 19. So that switching from here to there was done by applying 30 volt DC apply here. Now the point of showing this graph here is that the sample which was already homotrophic or vertical state, if you apply a field, nothing will happen because they are in the same state. So no change will happen over there. This is one more, this is quantization, that how we can understand. So you can see here that in this graph at the right side, you can see that this black point 0 and 30 volt, they're trying to overlap somewhere here, like see. So and the top one basically already for this the voltage, and the black one belongs to the without applying voltage. So they are showing that that we are in the right condition. Now one more thing is very important to understand. Whenever we try to add something in the matrix, we have to worry about everything. हमें फायदा हो रहा है तो हमें फायदा ही हो रहा है, नुकसान भी कुछ हो रहा होगा. So वो क्या हो सकता है? Now because as we all know that carbon dots are very conducting in nature actually by default. So they will do something on there. So what we did, we try to understand what happens to conductivity of the material or the composites. So for that, you can see here there's a graph plotted between X, again the frequency and the conductivity over there. And it's a very interesting to see here on this that if I pick up this pure sample here, this is starting from here to there and goes up like this. So this flat portion, which remains independent of frequency, That is going to give us the DC conductivity. We can call it ionic because there are ions available in the matrix. Now, after certain frequency, this shoots up and goes up with the frequency. That is called the AC part. Now, when we add it, you can see here for this one, last one, 0.5, we can see that this is part goes up and then again this like this. So this part, what we see, the first one here, this is coming because of the electrode polarization. So we are having three reasons here: electrode polarization and DC conductivity because of ions, and then of course we have the AC conductivity part over here. There's a very famous law. This is called JPL. We have fitted that equation, and we can also do other things here. So this is further characterization. We can also understand the conductivity with temperature variation, how it happens here, and of course we can also calculate this. This is called the accretion energy for that process happening for the conductivity change, and this will also show the this kind of variation. This again coincide with the change of the alignment from planar to vertical. This is one of the important slide. I mean, this is schematic diagram to understand how to explain our results. You can see here in the beginning, the figure number A, simple diagram, which again shows that if you anchor the substrate planar condition, all the molecules will align on the plane, as you can see over there. Now start doping with small amount, because they are very small in number, concentration, what they will go inside and they try to perturb the alignment. The B, if you go more medium, so what happens? Some of them will start settling down the bottom, and some of them will still remain in the same. But as you go little higher, what happens? You will get a condition where you have enough number of carbon dioxide in the substrate, and they will try to actually break this anchoring, and that start. They're starting like this. They stand up here, and this will start to propagate further. This is called the called this sub-assembly process, and then it will maintain the entire alignment over there, like this. All right. So this is simply diagram. I said in the beginning, what we said, we have a sample very planar anchoring. We got this kind of change. Now we tested what happens if you remove alignment layer. No alignment layer in the beginning itself. So what we found that it is showing this kind of tendency, but when you add on something more, it becomes little more better condition. But if you go further up, it starts degrading. This is for pneumatic. Let me go to very quickly to the second sample where we have pneumatic and symmetric A phase both. This slide shows the symmetric A phase. Again, I repeat, symmetric A means it has a layered structure. You have pneumatic ordering, and then you have layer ordering also. So viscosity is going to increase over there. And when you have a layer, then it's difficult to align them also again. But what we found that as we increase the concentration, you can see here at 0.25 and beyond, the sample texture becomes dark, means it is changed from planar to vertical. When you heated sample up to pneumatic phase, this also shows the same story. It can be changed. What we found in this sample, which has planar alignment, we added this carbon dots. It gives the same result what we found in pneumatic phase. This is again same thing, confirmation with the dielectric measurement. I can show you from symmetric A and the pneumatic phase at 0 volt, and of course at the different higher voltage condition. One more thing here, we are showing here that if you try to plot this dielectric loss with frequency, you will see that certain relaxation happening over there, and this corresponds to the short axis relaxation of the molecule that we have in pneumatic phase. That's again confirm this vertical alignment. This is the graph where we can understand that once we have induced this alignment, that remains stable throughout the pneumatic and symmetric. You can see here all those points on the top, they remain the same pattern. This is the simple behavior again. This slide actually shows, you can see visually what happens when you are in the symmetric A phase and the symmetric A phase and the pneumatic phase. You can see that you start from pure 8 CB, apply voltage. So where we don't have nanoparticle, they will switch as usual, they have to be. But in the case when you have this carbon dots, you may require little less concentration, little less voltage to switch on that. And the thing which are already in vertical state, they don't show any change because they're already in vertical state. Same thing we can realize from the pneumatic texture that shown are there. This is again the conductivity thing what I showed in the previous sample. You'll get the same kind of confirmation over there. This is again this thermal behavior of conductivity, and we plotted this accretion energy also. Then next, this is a good point to discuss here again. Please look at on the screen. On the left panel, I have shown you symmetric A. Can you see this is a this is plate, a layer. These lines what I draw there, this is called layer. So what happens? Suppose this is for the bottom plate, So layers has to arrange like this. Means layers will grow vertical to the plate and the molecule will come like this. What you can see there. Now think about it. If I want to change the molecule from this to this, means to do that, I have to ask this layer first to come from here to there. Then only the molecule can stand up. So can you think this will cost a lot of energy? But these carbon dots have that power that they did the job. So what you can see here, that then they will change. First these layers will become parallel to the plate and the molecules will stand vertical. So that's how this change. Pneumatic, as discussed earlier, the same story. Then this was for unaligned sample. We obtained a similar kind of result, but something like that. Then one more thing. There are two kinds of material. I hope I'm very much clear here. One is called positive dielectric, negative dielectric material. So this is a very like some very what do you call it? It's particular information, but I want to tell you that there are two kind of materials people use in the field, negative and positive, depending on the requirements. So this example I'm showing you, this is called the negative dielectric material on pneumatic phase. So in this case, what we found that when we have this delta epsilon negative, if you use unaligned sample, means there is no alignment layer in sample cell. You can see here the figure number A. This picture is very well known picture. It's called cylinder texture. There are defects, 4+ defects are there. If you look at pneumatic, type pneumatic in Google and find the picture, you will find this picture. It's a well-known picture of cylinder texture. So no alignment, do we get this? So we're sure. But can you think we are added only this much 0.002%? It starts changing the alignment from unaligned to trying to become vertical. And of course at 0.01 this becomes fully vertical state. So we have induced, so the carbon dots have the capability to induce this kind of alignment, which is very much useful. This was confirmed by the VT graph and then dielectric permittivity results. This slide shows again the stability of the alignment which is induced. That shows that this alignment induced remain the uniform state throughout the pneumatic phase. This is the yes, I'm done. So this is simple diagram to understand how the molecules are getting oriented in vertical state even when we do not have an alignment layer. So you can see that these carbon dots have this long alkyl chain. So वो जो molecule हमारा है आके वहाँ पर tag होगा, first बीच में ऐसे आता है, so then it start vertical like that. And this was simply again the same characterization to understand conductivity. But one more point, these negative material, what we found in the case of negative material, if we are using the planar anchored sample cell, they are not doing anything with that. While in positive material, whether you use planar or unaligned, in both cases they were able to change the alignment to vertical state. So this is the conclusion what I discussed over here, that basically in the case of positive valence materials, we can induce the alignment from planar to vertical with low concentration, but in negative material, we can get this kind of result only with the unaligned sample cell. And so what is the last point, only one sentence, what is the outcome, or what is the role, what is the use of this kind of result basically? So I believe we all are aware about sensing devices and so on and so forth. So in that case, or display. So if you go and read about LCD, you will find that all LCD has alignment layer to work on. So we can remove that layer and to have the alignment also. In sensors based on liquid crystal material, they also need alignment layer. One can remove the alignment layer and make the sensors. That is the application point of this. Sorry, only one slide. This is very important because I came here to. Yes. Yeah, this is very important. Please bear with me one more minute because I don't get this thing again and again. I will acknowledge first of all, Dr. Priscilla P. She was my first PhD student. Currently, she is working at Taiwan as a postdoc fellow. She did all this work what I presented today. And Sandeep Kumar sir, who gave these carbon dots to us. Then of course, Dr. Suprita Reddy here, sitting here. She is my collaborator. And Dr. Jayaprakash, Dipanshu Varsne, Praveen Malik sir, Ashwini Kumar Singh, and of course at the last and not the least, my HOI. He is Dean and Science Doctoral Domain and Director of my own institution where I work actually at MIT Noida. This is my national list. And on the right, you can see there are some people over there. They are from international collaborator. Dr. Michael Fish is there from Kent State. And the remaining two, Ricardo and Daniel, they're from Italy, where I was there in long back. So, and with that, I also acknowledge the funding that we have received from CST UP and SALB Sure. She is the PI sitting over here. I am the co-PI in the project. We have done a wonderful job. It's already going on last year. So this is my group. at the MIT. And the right also, I am also sharing with Dr. Supreet, two students for the PhD program. Thank you very much for your kind attention.
So thank you, Professor Gautam. The talk is open for discussion. Any question from the audience? If there's a one question.
Good afternoon, sir. My question is how the shape and size of nanomaterials can affect the physical properties of pneumatic liquid crystals.
So you can take that. Actually, as I said in the beginning, that LC materials, the molecules are the shape is anisotropic in nature, means they will show the property depending on direction. Now, once we have this system, I see saying, suppose I'm going to put spherical particle. When a spherical particle will go, it will have different effect. If I am going to put rod-like molecule, so rod-like, suppose CNT is rod-like molecule. Now CNT has more similarity with the LC molecule, so it will differently. So it will may have more positive impact. But same time, CNT has little longer, like size quite bigger, so hard to control their dispersibility in the LC. Dots are very small, less than 10 nanometers, so it's easier to work on there. So definitely, people are trying to infuse this 1D nanomaterial, let's say, carbon nanotubes and so on and so forth. But the problem comes at the end that whether they're dispersible or not, they're stable or not. So the stability is more concern. Thank you.
So if there is no more question, let's thank. Oh, there is one more question.
Yeah.
Good morning, sir.
Very good morning.
Sir, I want to ask that you mentioned about the applications of carbon dots. So I want to ask that what is carbon dot helpful in cancer detection of cancer, treating cancer?
I think if I recall, while reading all these things, I came across that definitely they are very much useful in different kind of treatment, maybe in the cancer as well. I'm not sure exactly, but definitely they are being used. The HeLa cell and all they have been properly used, and they are very good because they are, they're very cost effective, eco-friendly, and non-toxic in nature. So that is the main major point of this carbon dots among the other semiconductor quantum dots. So people are trying to implement that. So we have taken that and trying to work with our field, the liquid crystal. That was the idea.
Okay, thank you, sir.
So if there is no more question, let's thank Professor Gautam for such a wonderful talk on liquid crystals. Thank you, sir.
Thank you so much, sir, for such an insightful talk. Now I would request Professor Ankush Roach, Professor Thakur, to please felicitate the guest. I request आगे आ जाओ थोड़ा सा बस
So now let's move to the last talk of this session before lunch. And we have now with us Dr. Alankrit Tomar. Dr. Alankrit Tomar is an optical system engineer who completed his PhD from the University of Texas at Austin, United States, in electrical and computer engineering. His doctoral work focused on developing optical microscopy technique for brain imaging, a field that combines the precision of photomics with the ambition of neuroscience. Dr. Tomar has authored several research papers in reputed journals and has presented his work at conferences across US and Europe. He was awarded the prestigious Genlab Young Investigator Award at SPIE, a recognition of his exceptional early career contributions to biophotonics. Beyond fundamental research, Dr. Tomar is passionate about translating optical technologies into scalable frugal solutions, particularly for healthcare diagnostics and environmental monitoring, aligning directly with the Global Sustainable Development Goals (SDGs). So we'll be talking today on for sustainability from advanced imaging to solutions. So, Dr. Alankit, can you hear us?
Yes, I can hear you. Can you hear me?
Yeah. So you can share
Uh,
your screen now.
yeah, I'll share my screen. Can you see my correct screen?
Yeah, we can see it. You can make it in full screen mode.
Okay, can you see my present?
And you have start and
Is
you have
that
30 minutes to conclude.
sorry? I can't hear you. Is that the right screen?
Yeah, we can see it.
Okay. Okay, cool. Okay, let's begin. Good afternoon, everyone. Sorry, were you saying something?
Yeah, 20.
I can't hear you. Your
Okay.
voice is getting cut out.
You can start. We'll interrupt him.
Okay, if there's anything, just let me know in the chat. I'll be following the chat. Uh,
So you can
okay,
start the presentation. The timing for the presentation is 30 minutes.
okay, cool. Yeah, I'll be done in 30 minutes. Good afternoon, everyone. I am Alankrit Tomar, and thank you so much to the organizers for giving me the opportunity to present at this conference. Dr. Gautam, it was very nice, looking at your research that you've been undertaking. Today, I will be talking about how photonics can be used for sustainability, specifically for the UN Sustainability Development Goals. And I will be doing that by taking examples from my own PhD work, as well as a review of other other research work that has been undertaken by other groups across the world. So a little bit about myself first. I completed my schooling in 2015, and then in 2019 I completed my bachelor's degree in engineering physics from Delhi Technological University, which was earlier Delhi College of Engineering. After that, I started my PhD at the University of Texas at Austin. And my PhD was in the Department of Electrical and Computer Engineering. And since then, I've been working in industry. So, like a lot of you might be aware in the audience here that photonics is the interaction of light and matter. And it essentially means that how radiation in the UV range or visible range or near infrared range interacts with matter. And the applications of photonics are numerous, in a lot of fields such as medical devices, environmental monitoring, connectivity. You all of us have been following the AI surge these days. We use ChatGPT, Gemini, and all of these have been enabled by research in photonics. But today's talk will be focused on a very specific part of photonics, which is microscopy, which is what my research was in. And I'll be taking examples from the field of microscopy by other researchers as well. And I will try to by the end of this talk, I will try to convince you all that how photonics can be used towards these three sustainability goals, which have been given by the UN. And the three goals that I'll be talking about today are one, the first being good health and well-being, the second being life below water, and the third being quality education. And like I said, I will be taking examples from academic research as well as a field called frugal science or frugal engineering. So before diving into each of these sustainability goals, I wanted to give a little background into what the difference is between advanced research and frugal engineering. So I have a graph here which shows on the x-axis the cost of any device, and on the y-axis is performance. So let's say we are operating at this area, which is high cost but low performance. So an object like that will be undesirable. A device like that, invention like that will be useless, right? Something which is high cost as well as high performance usually falls in the realm of advanced research or a commercial product. And if we go into this region of this graph, which is low cost and low performance, is a term that you all have heard. It's called jugaad, and it's a very popular term for coming up with innovative solutions in India. And you will agree with me that this is a low cost solution to a problem, but it does not have the performance that you need. But let's say the cost is low and your performance is also pretty high. This is the area of frugal engineering or frugal science. And I'll be taking some examples from the field of both advanced research as well as frugal science in my frugal engineering in my presentation today. So just to make the point a bit clearer, the difference between jugaad and frugal engineering is that frugal engineering is repeatable and reproducible, which means that a solution that I make today here, sitting, let's say in the US, should be able to be replicated and repeatable by you sitting in India. And that is frugal engineering. Jugaad is restrictive to certain areas, certain resources, and I would not specifically call that engineering. So let's keep this difference in mind when we discuss the frugal engineering solutions that I'll bring up. And I want to, before getting into the details, I want to make it clear that I have not particularly undertaken any research in the field of frugal engineering, though I've been closely associated with this. I will take research examples from other groups across the US, and I'll try to convince how frugal engineering can be used for the sustainability and development goals. So the first one that I want to explore is good health and well-being. And in this area, the UN has given us three main, actually a lot of many targets, but I'll be talking about three specifically. The first one being premature mortality from non-communicable diseases, such as cardiovascular diseases, stroke, diabetes. And in order to give you more insights into this, I will be taking parts of my research and explaining them more. So this research was undertaken as part of my PhD project at University of Texas at Austin. And this project relates to brain imaging. Brain, as we all know, is a highly complex organ. It only occupies 2% of the mass in the body, but expends about 20% of the energy. And at the core of this brain organ is this functioning body called the neurovascular unit, which consists of the neurons and the blood vessels in the brain. Whenever there is a neuronal activity, let's say a functional activity, let's say you're trying to sing or you're trying to play cricket, there is firing of neurons in the brain. And around those neurons is an increase in the blood flow, which is called hemodynamic response. So both the neurons and the blood vessels operate together to give us the functions that we desire. But in a lot of diseases, this linkage or this coupling between neurons and blood vessels gets disturbed. And these include Alzheimer's disease, Parkinson's disease, and even COVID-19. But in my PhD, I focused on stroke and how the brain was impacted in the event of a stroke. The stroke is a third leading cause of death in India. Annually, 18 lakh strokes occur, with a death occurring every 4 minutes. 1 in 6 people get a stroke in their lifetime across the world. So as you will imagine, this is a big problem, and it falls in the non-communicable disease target that UN SDG has been talking about. So, in order to understand what happens to the brain at this micro level of the neurons and the blood vessels, we need imaging technologies, or we need modalities that can image the brain at the resolution of the individual cells and neurons in the brain. So the goal is that we want to image the blood vessels and the neurons at the micro scale to get an idea of what happens to the brain and these cells and blood vessels when a stroke occurs. And this is where my PhD project comes into the picture, wherein I used a microscopy technique called two-photon microscopy for in vivo imaging of the rodent cortex. And for this, just to put this in context, I've shown a graph here which shows many imaging modalities. And I'm sure you will have heard about these sometime in your life. So on the right side of the graph is a imaging technique called MRI. I'm sure you have heard about MRIs. An MRI can give you a scan of the whole brain, but it cannot give you details of the individual cells in the brain. On the other end of this graph are microscopy techniques which can give you an idea of the single cells in the brain, but it will be very difficult to map the whole brain. But two-photon microscopy is that technique which can give you resolution of the micro vessels and the neurons, as well as a large part of the brain. And this technique is called two-photon microscopy. So in my PhD, I undertook brain imaging of the rodent cortex, which means I did imaging of the mouse brain. As you might have heard, that mice share 95% of their DNA from humans. So if we can understand how the mouse brain functions, we might be able to understand someday how the human brain works as well. And that is the motivation for doing research with mice. And I will not go into the detail of my microscopy technique because it is beyond the scope of today's talk. But I would, if you want to read more about it, you can reach out to me, or I have published papers online. You can look those up. So by using this microscopy technique called two-photon microscopy, we can create these beautiful 3D network of the mouse blood vessels inside the brain. So what you're seeing is a 3D volume of the blood vessels of a mouse, which is imaged while the mouse is alive. And this is what two-photon microscopy can help us accomplish. And by using these 3D volumes, we can create computerized models of these, which can help us understand what the brain looks like on a fundamental level, how the brain gets impacted in the event of a disease like a stroke. And further, this microscopy technique can help us create drugs for treatment of these non-communicable diseases, let's say, a cardiovascular disease or Parkinson's or Alzheimer's. So this is where my research, which is an example of an advanced academic research, can play a role in advancing the UN SDGs. And the first one, which I've discussed, is premature mortality from non-communicable diseases. So in the second part of this goal, I would like to focus on the two targets shown here in bold. One is related to the epidemic of malaria. And the second is strengthening the capacity of all countries for early warning of global health risks. And I'll take examples from the field of frugal engineering. And like I said, this is not my research. This was undertaken by the lab of Dr. Manu Prakash from Stanford University. Throughout this talk, I will explore more projects of Dr. Manu Prakash, and I highly and strongly encourage you to check out his work. He is an inspiration to all engineers and scientists, and he shares a close connection to our country as well. So here is a graph that shows the number of people killed by animals per year. So sharks kill about 10 people every year. Dogs kill about 25,000 people every year. Humans kill about 475,000 every year. But it is very surprising that none of these are the world's none of these rank as the top deadliest animal in the world. The deadliest animal in the world is actually the mosquito, which kills about 7,25,000 people every year. Like I said, malaria is a big problem, and it also forms part of the UN SDGs. 94% of all malaria cases and deaths are reported in the African region. 67% of all malaria deaths are of children under the ages of 5. So you can imagine that this is a big problem, not just in Africa, but also in India as well. So the main diagnostic technique, the way to detect malaria currently is manual microscopy. And what this involves is that, a blood sample is taken of a person, a slide is created, and a person sits at a table under a microscope and investigates the blood sample. And this process is really slow. And, because of how humans operate, a person can only look at 25 people every day. So you will agree with me that this process is not efficient at all. So there is a need for low cost, motorized, high throughput diagnosis of malaria. And I'm sure all of these terms are self-explanatory, where you want a low cost device, a device which is efficient, motorized, and high throughput. It gives you analysis of large number of blood samples. So the lab of Manu Prakash has come up with a modular microscope, which you can put together like, Legos, or, back in the day, we had something called mechanics. I'm sure a lot of students in the crowd must have built that. It consists of, so this device, which is called the Octopi, consists of different kinds of imaging modules, illumination modules, and scanning modules. And you can just pick and choose. You can choose a low magnification imaging modules. You can put it on top of the sampling stage, and you can use any illumination technique possible, such as bright field microscopy or fluorescence microscopy or dark field microscopy. And this is and I'll show a video later, but this is a very small device, and it's portable. And these devices also function on a local computer or processing unit, such as a Raspberry Pi or an NVIDIA Jetson, etc. And these devices are made in a way that they can operate with solar light or a very, very low power requirement. So here is a video of the Octopi. Let me see if I can play this. Okay. So what you will see here, a slide is loaded on the scanning module. Then with the help of magnets, the imaging module is latched on. And then you can just investigate the blood sample, the cells in the blood sample at a really high speed. You can investigate about 1 million cells per minute, which is way faster than what a human can investigate. So you can see all the green that you saw were actually malaria parasites. And you can see how simple this device is. And it's a low cost device. It's only $200 to $300, $500, and it's 3 kgs. So you can carry this to a rural area, put it there, and people will be able to, some technician will be able to use it very easily. Okay, so like I said, that the process of creating these, using this microscope involves creating a blood slide and then staining it, and then you will be able to see different organisms, as you can see in this image below, different worms or organisms are being caught by this microscope. So this is an example of frugal engineering, where they have used low-cost motors. They have tried to use some tricks in the field of optics to create a device which can operate without internet, without a lot of power. It's portable, it's low cost. And this only comes when you observe things around you. For example, Dr. Prakash was mentioning once that the first stages that they used in this were taken from DVD players. You have DVD player, which is, back in the day, the CD player used to come in and out of your CPU. That is a stage that can be repurposed for a concept like a microscope. So, taking inspiration from things around you is the core essence of frugal engineering. With this, I come to the second part, which is life below water. And one of the targets under this SDG is to increase the scientific knowledge, develop research capacity pertaining to marine biodiversity. And at the core of this target is this organism called planktons. Planktons are essentially microorganisms that are floating in the ocean, and they play a crucial role in marine food chain and oxygen production, to the extent that they create about 50% of Earth's oxygen. And as you know that 97 of, a large percentage of the Earth's volume comprises of water. So the volume of these organisms must be really high. And it is important to understand the life cycle of these planktons and how they operate to get a better idea of the quality of the seas that we have on Earth. So in order to understand this large volume of planktons, again, there is a need for a low cost, high throughput, quantitative microscope to study planktons. Something which is low cost, helps us get an idea of a large volume of water, and which is quantitative in nature. So again, the lab of Dr. Manu Prakash has come up with a open source imaging platform called Planktoscope. So a planktoscope is a device which can be used for investigation of the contents in the water that you use to flow through this device. So in this is the device here. It's a very small, compact device. And this is Dr. Manu Prakash. He's taken this planktoscope to Lake Chilika, where he's investigating water samples. And this is what the stack of this entire device looks like. It's pretty simple. And again, I won't go into the details. This is a published paper online. You can look it up and read more about it. It's very clearly written, and it should be very easy to understand. So you have a pump, a peristaltic, very basic pump, which is very low cost. You have an illumination module. Again, modules are very cheap these days. You have linear stages, which are controlled by Arduino. And the details are in the paper, but they made this entire stage system in about $30 or so. You have a bunch of very small optics, and you have an imaging sensor. So when you put all of them together, water can flow. You can place a water sample, water can flow through this device, and you can investigate the contents of the water. This is an advanced version of the same thing, and this is what it looks in a very nice and refined product. So once you get images out of this device called the planktoscope, then you will be able to use some image processing techniques to extract the organisms from these images. So you can see that, in image one, they just get some images, they run some processing, and then they're able to identify the individual organisms in this large picture that they have. Then they can put all of these organisms in one entire database called the ecotaxa, and they can classify the organisms depending on their shape, their features, etc. And this gives us an idea of, what the life of the water body is, what the quality is. And so one example that I think is, let's say you go and take a sample of Yamuna. and you do that a lot more times, many people do it, and you find that there is one organism that is present more than others, so then you will be able to correlate that the quality of the Yamuna River with the presence of these organisms. And this is the basis of any scientific experiment that you do. So the goal of an instrument such as this is to give it to the people so that they can use it on their own, not just you, but like marine biologists, engineers, etc. And these devices are made so simply that if you want to use it for some other purpose, let's say you don't want to use this imaging sensor, you want to use a different camera, you can easily modify this to, you can remove this last part and install the new sensor here. So all of these devices are made in a way that upgrades are really easy. And that is also the core of frugal engineering. So if we compare the planktoscope to a commercial product, like I had shown in that graph, a commercial product is a device which is high cost, but it also has high performance. So let's compare the performance of the planktoscope with a commercial product which does the same thing called the FlowCam. So the FlowCam acquires about 5,400 images. Planktoscope almost does the same thing too. There is a difference in the performance, but not by a huge factor. But you can see that the cost is significantly higher. It's more than 100 times. So this is really important to understand that the cost of commercial products, the performance of commercial products can be really high, but the cost will also be really high. So the goal is to create high performance with low cost so that it is more accessible. Okay, so with this, I come to the last part of my talk, which is related to the UN SDG goal of quality education. And under this goal, there are a lot of targets which involve an aspect of equitable, accessible, and quality education. You need to be able to provide education to all children, irrespective of their gender, locality, language, etc. So this is Dr. Manu Prakash, and this was his student Jim. And they started with the basic idea that they wanted to give a microscope to every child in the world. Now, microscopes are one of the most expensive items in the field of photonics or optics. They cost thousands and lakhs of rupees. So they started with the goal of how they can create a microscope which can be accessible by every child in the world. And this is an early sketch of a microscope called the Foldscope. And this is what it looks like. It is a paper-based, low-cost microscope. How it works is, and you can again read a paper, the paper about it, but it consists of folded paper, cardboard, which you can just assemble in a very easy manner. It comes in with a small lens, with a small light, very cheap light source, and it can be used to investigate a lot of the organisms that you will be able to also see with the high cost microscope. So the Foldscope is a paper-made microscope, which is made by which is aligned by folding. So it's an origami-based paper microscope. It has micro optics, it has small lenses and illumination. It is very easy to assemble and it is low cost. So by using this Foldscope, you can do a large number of microscopy techniques, such as bright field microscopy, fluorescence, lens arrays, dark field. So the opportunities are endless, just with a simple $100 microscope, which is made out of paper. And you can also, so these are some images from, which were taken using Foldscope. You can see that you can zoom in at pretty high magnification. This is an image of the leg of a ladybug. This is an image of the leg of an ant. So the goal is that, every child should be able to visualize the microorganisms which are all around us. And that is the whole purpose of the Foldscope. So here is a breakdown of the price of the Foldscope. It's a paper-based microscope. So, paper is abundant. It's really low cost. They have used a ball lens, which is again a very cheap lens. It comes about 20-30 rupees. They have a 3-volt button battery, again, really cheap, very cheap LED, and a switch. Just give me 1 second. Sorry about that. My charger disconnected. Yes, so this is the breakdown of the Foldscope. And, across the world, there are about more than 1 million Foldscopes that have been built. Teachers, educationists run workshops to teach people how to build a Foldscope. Foldscope is accessible to a large communities, irrespective of the financial resources that they come from. And I think this is a really inspiring moment, and should encourage all of us to start to think about what we can do, about the problems which we see around us, and which are also related to the UN SDGs. So with this, I come to the end of my talk, wherein today I have taken examples of research undertaken in the field of photonics and how they are used to advance the UN SDGs. I would like to end by simply talking about some actionable things that we can do. Throughout this conference, you will hear a lot of great talks, you will hear a lot of research, but you should take away with certain actionables, like, what are you going to do tomorrow, day after? And what do you take away from this entire research? From my perspective, I have a few things to share. So for the students who are attending this conference and who are undertaking research, I would like to encourage you to observe and think deeply about the problems around you. The problems of lack of quality education, or, medical health, lack of medical health is not new. They're all around us. But we need to sit and observe what is happening in these problems and think deeply how these can be solved. Next, I want to say that start small. Don't think about changing the world. Start at your local level and think frugally. Don't think about jugaad. Don't think about how I can make a makeshift solution. Think about how I can engineer something which somebody else in some other village or town can also use with the resources they have. So for professors and advisors, again, I feel that we need to start finding value in projects that might not need to immediate outcomes, right? There are a lot of research that can be done to solve society's problems that might not have immediate outcomes. And we need to encourage open-ended discussions about the UN SDGs, and specifically what problems which are discussed pertain to India. For departments and universities, I think there is a need to incentivize project research that tackle the UN SDGs initiatives directly, and for promoting grants for frugal engineering. I think all of these would help us better move towards solving the problems which have been proposed in the UN SDGs. Thank you so much for listening. Thank you all the organizers. And if there are any questions, I'll take those now. And you can also reach out to me at this email. Thank you so much.
Thank you, Dr. Tonu, for reminding us why science matters beyond the journal page. The ambition to make photonics accessible and impactful is truly inspiring. Now we'll have Vishal Singh Chandra's presentation with us. Are there any questions? We have Dr. Tonu, we have a question.
Yeah, sure.
Good afternoon, sir.
Hey, good afternoon.
Yeah. So you discussed about two photon imaging. So you discuss about diseases like stroke, Alzheimer's, Parkinson's. So I want to ask, can it help in study of neuroplasticity in mental health disorders like anxiety or depression?
Yeah, absolutely. So, I mean, like I said, we are investigating diseases from a broad perspective, like what happens on a large scale in the brain. But a lot of the diseases like, anxiety, depression have very have are formed due to abnormalities on the individual cells and neurons in certain parts of the brain. So a technique like two-photon microscopy can help you image certain parts with high resolution, and thus it can help you provide more insights. And I'm sure there are more papers on this. So yes, you're right. They can be used. I would like you to read online. I'm sure there are papers about this.
Thank you, sir.
Dr. Tomar, the four scopes you were talking about, are they available in India?
Yes, absolutely. They are available in India. They ship and it's very cheap. So if and they actually send a bulk order. So if you want to get hundreds or so, the shipping cost reduces. So
Is
you
it
can actually get those for your entire department, and turns out to be a very cost-effective option. And a lot of people in India are actually, have a lot of Foldscope available with them already. So you don't have to ship them from the US. So
is it
it's a you can look
possible?
it up.
So is it possible to order them online?
Yeah, absolutely. So foldscope.com is the website, and you should be able to order them from there.
Okay, thank you so much.
Yeah.
Thank you, Dr. Tomar.
Yes, thank you so much.
This one? 5 minutes. हाँ जी sir, 5 to 7 minutes.
Still work or?
This works.
First of all, I would like to thank the organizers who have accommodated me in this busy schedule. And I already know that it is already lunchtime and nobody is willing to listen, anyone. So I will try to complete this talk in 5 minutes. So much have already been done by very good researchers, and this work that I'm going to present here is done by the BTech final year students, and you will enjoy it, I think. So outline of my presentation is what is SDG, why sustainability, because your topic is associated with this topic. Then specifically clean water and sanitation, types of pollutions, dyes, why this particular material Santa Maria Pure Fuse, it is a plant. What are the remedial actions, synthesis and characterization for this copper oxide nanoparticles, result in discussion and conclusion. Ma'am, this is not working. Okay, sorry. There are 17 SDGs, it is well known to all of us, and there are almost 169 targets which were given by UN for this SDG, and I am going to deal with only one specific, that is clean water and sanitation. There are certain things which are written here. No, because of lack of time, I will not discuss this. Why sustainability? Sustainability is a buzzword for the last few years, and pollution in water bodies due to untreated sewage, industrial waste, and uncontrolled use of pesticide, dyes, etc. It is there. Use of materials, items, plants which have negative effect on environment, and no economic values can be used for this problem. Types of pollution I am not going to deal with. Now the pollution in water bodies due to dyes. Dyes are used in various places. I missed my introduction. I am Dr. Vishal Singh Chandil from Engineering College. It is a remote engineering college in UP. It is in Ambedkar Nagar. And close to Ambedkar Nagar, there is a town known as Tanda, and Tanda is very big hub of textile. So dye is a big problem there. So I have taken the data for this specific town, Tanda, which is close to Ambedkar Nagar. So you can see there is a lot of pollution because of dye which is used for textile industry alone. There are various dyes. Because of, again, the lack of time, I am not going to deal with this. You can see the dyes are used in various fields, various places.
So you cannot eliminate them right now. So we can reduce them, we can get some solution for the wastewater treatment, but there are various medical reasons that you have to reduce them. The skin irritation, allergies, respiratory problems, eye and mucous membrane irritation, carcinogen effect or endocrine problems are there. So this is the problem which is because of dye. There is one more problem because of a weed which is known as Santa Maria feverfew. It is well known as carrot grass or gajar grass. You can see it is abundant everywhere, in even close to your campus also. This red region is showing the spread of this weed because it is very invasive, and I have taken the Indian continent, especially UP, then specifically the city Ambedkar Nagar. So again, it has very harmful effect. The major problems associated with this is it is very aggressive. It is harmful to livestock. It has many various health results. It produces various kind of risk. It dries very quickly, so there is a problem of fire also. If you wish to control it, there is high cost associated with this. So this is again a problem. So first problem will be resolved with the help of second problem. How? We will see it. Now as we are going to use some material which will work as photocatalyst. So one slide for this. What is photocatalyst? It is a material. Photocatalysts are the materials that decomposes the adverse substances under the sunlight. Why sunlight? Again, because it is abundant and it is free of cost. There are various advantages of photocatalyst. You can see it. Some example of photocatalysis, what is happening in presence of light when a material which is known as photocatalyst is used. So again, these are some simple slides, specific slides. Why green synthesis? Green synthesis is eco-friendly and cost-effective. It uses various things. I have taken, in this case, I have taken leaves of the Santa Maria feverfew plant. What is how it has been done? It is collected. We have collected Santa Maria feverfew leaves, dried and washed with distilled water, dissolved in distilled water, heated for 70 to 80 degree till reduces to half of its amount. Then it was filtered with the Whatman paper filter number 1, and this extract was used for sample preparation. Sample preparation is again very simple. In this case, we prepared 0.5 m solution of copper sulfate pentahydrated. It was analytical grade, high media. It was dissolved in 50 ml of water. And there is certain steps which are usual in preparation of nanomaterials. These are usual things. These can be tailored for a specific size or shape. So characterization technique, again, there are certain specific things. If you are synthesizing any material, the first step is to get the X-ray characterization, then size, shape, morphology, and specific values. So this is the XRD of copper oxide which was synthesized, and here you can see there are two phases, Cu2O and COO both are present, and from the peaks we can say that the major peaks are for CuO, so the dominance in the material is of CuO. FECM images, you can again see they are agglomerated and spherical shape is there. With the help of SECM, again EDX analysis can be done, and with the help of ImageJ software, the particle size distribution can also be done. So again, it is clear that the presence of copper and oxygen is there, and average particle size is around 45 nanometer, and it is in between 20 to 80 nanometer. FTIR characterization is again done for the fixing the whether the compound is properly synthesized or not. Again, this is very essential part that is going to be used whenever we are using any metal oxide. Simple UV visual will not work many times, so we use diffuse reflectance spectroscopy for getting band gap and other things. So otherwise, if it is not, it is dissolved in a normal thing, we use UV visual spectroscopy. Further, the practical application of these nanoparticles, which was prepared with the help of Santa Maria feverfew, was done for photocatalytic degradation of methylene blue dye. In this, we have used 8 milligram of copper oxide with 3 milligram of aniline blue, and it is graph are well interpreted that in presence of copper oxide, and with respect to time, you can see for 120 minutes it was well degraded, and it is around 91.11%. And I think I missed the slide. The repeatability was done by the students, and it was around 70% up to 3 cycles. So we can conclude that Santa Maria feverfew, it is a very big problem for farmers. Its leaves can be used for green synthesis of copper oxide nanoparticles, may be used for some other particles also. And these nanoparticles were further used for photocatalytic degradation of aniline blue dye. Average size was around 45 nanometer, and with the help of UV DRS, band gap was found to be 3.56 electron volt, and degradation of aniline blue was around 91.11% in first round. This paper was published in some Scopus journal. I am thankful to TCUB 3, UPCST, AKTU Lucknow, REC Ambedkar Nagar, and MIT University Noida also, and other team members. Thank you.
Thank you, sir. Do you have any questions?
बहुत तेज बोला तो हो सकता है कुछ समझ में ही ना आए. Anyone?
Thank you.
No. डायरेक्ट सोर्स से अगर लेंगे तो डायरेक्ट सोर्स में क्या क्या कंटामिनेशन हो जाता है, और डायरेक्ट सोर्स से अगर लेना है तो फिर वेस्ट वाटर ट्रीटमेंट के लिए फिर अलग इफेक्ट्स है और उनको अलग तेल की जो हमने बनाया है वो उस पर्टिकुलर पे सही डेटा पर्टिकुलर एक डाई के लिए किया गया है, पर्टिकुलर एक डाई के लिए किया गया है. और जब आप टेक्सटाइल हमने जो प्रॉब्लम बताई फोटो नहीं हटा रहे हैं, ये डाई की वजह से जो प्रॉब्लम क्रिएट हो रही है इसको रिमूव करना है वाटर से कर दो, और उसको रिमूव करने से हमारा बंद मत कर आंटा मरिया कैरेट क्रॉप उसको यूज करना है. तो दो विन विन सिचुएशन है, उसको यूज करना है, इसको रिमूव करने के लिए नैनो पार्टिकल बनाने के लिए बहुत सारे मेथड. तो कोई ऐसा मेथड यूज करें जो कॉस्ट इफेक्टिव हो, इसमें आपको कोई दूसरा रिएजेंट नहीं चाहिए, सिंपल कॉपर ऑक्साइड पेंटाहाइड्रेट. आपने बताया अभी मैंने पर्टिकुलर सेल्स डाइग्रेडेड करने के लिए मैंने अपना पार्टिकल डाला, तो ऐसा भी तो हो सकता है कि अगर जो पोल्यूटेंट्स हैं वो हमारे कंपोनेंट्स पे प्रभाव करते हैं ताकि हमारा डाइग्रेडेड अभी हो सकता है कि जो कॉपर ऑक्साइड है उसका फॉर्म चेंज कर उसको डिकम्पोज करके देयर आर ऑलवेज पॉसिबिलिटीज. अब स्पेसिफिक है कि अभी हमने एनिलीन ग्रुप पर काम किया, पूरा कोई स्टूडेंट का कोई टाइप भी कर सकता है, प्रोडामाइन भी कर सकता है, आर्ट्स भी कर सकता है. फिर जब आप वेस्ट वाटर में जाएंगे, वेस्ट वाटर के लिए देखना पड़ेगा कि वेस्ट वाटर ट्रीटमेंट में जब अगर एक्चुअल जो निकल रहा है पर सीपेज आ रहा है तो क्या उस पे करें वहां देखना पड़ेगा, और उसके बाद आपको कर चाहिए. अभी इसमें बहुत सारे क्वेश्चन आते हैं कि ये ऐसा क्या था कि तुमने नैनोपार्टिकल कर दिया, तो उसके लिए फिर हमको जीसीएमएस कराना पड़ेगा. तो ये बहुत ही छोटा प्रोजेक्ट था, फिर फाइनल ईयर के छोटा प्रोजेक्ट, तो हमें थोड़ा काम, तो हमें थोड़ा काम. लेकिन अगर आप पीएचडी स्कॉलर जब आप जाएंगे तो आपको कई सारे तब आपको वो क्वेश्चंस के आंसर मिलेंगे, या हमको भी वही तब हम दे पाएंगे ये करते.
Thank you, sir. So, ladies and gentlemen, distinguished guests, what morning it has been. We have traveled in the span of few hours from the quantum world of thin films, harvesting solar energy, to the mechanics of sound in microscale circuits. Versatility of liquid crystals. And finally, to the science corner in the world. This is stands for Frontiers Areas of Science and Technology for Sustainable Development. And today we have all seen all of it. Now I would like to topic to begin this.
Good afternoon, all. On behalf of the organizing committee of Fast ST 2026, I would like to express our deepest gratitude to our session chair, Professor Ankush K, which for his leadership and scholarly presence throughout this session. My heartfelt thanks to each of our speakers today, Professor Ayush Khare, Dr. Shubhadeep Datta, Dr. Umesh Kumar Dwivedi, Professor Gautam Singh, Dr. Alankrit Tomar, for their wonderful inspiration. You have gifted us your time, your knowledge, and your passion. For that, we are truly grateful. And to our wonderful audience, your presence, your questions, and your engagement are what give confidence like these their soul. So, thank you, dear participants, dear students, and faculty members who have joined us. Now, you to please join us for a group photograph. And also, session very nice.
I request all the distinguished guests and all faculty members to please come on stage. And students, once their photograph is done, after all that, please come on the stage too. हाँ ठीक है
Sir, please.
Let's assemble at the B block auditorium stairs for a group photograph.
And thank you to the AV team, Vivek sir and Shivam sir for supporting us, and to all the student volunteers. And students at registered students. Students are requested the registered students are requested to please join us for the lunch in the D block foyer, and after that for the inaugural valedictory session and the plenary lectures in D block auditorium.